Hello and welcome to Sleepy Science. Tonight we glide along the hush between questions and answers, where thought slows and wonder widens. Settle in, feel the weight of the day set down, and let your breath become a small metronome while we touch the gentler edges of quantum puzzles. Boxes that seem full without sharing, choices that wait for starlight, signals that coordinate without a whisper, and tiny records that quietly decide what becomes real. We'll visit cats that are only patterns, demons that pay for every scrap of knowledge, switches that let order blur, and games where honesty is proven by the way two silent rooms agree, not to dazzle, but to teach, clearly, calmly, how careful experiments build facts, how context shapes meaning, and how worlds are just sturdy tapestries of overlapping traces. If this soft exploration helps you drift, you can tap subscribe after you wake. But for now, simply breathe. Feel the bed hold you, and let curiosity idle low as we begin our quiet walk through 30 small lucid mysteries. Schrödinger's cat, reframed without myths. You've been told the cat is both alive and dead until you look. But if we're honest, that nursery rhyme version buries the real lesson. So let's keep the box, spare the cat, and use it to recalibrate how you think about what a quantum state actually is, and how small uncertainties balloon into stories about reality you can test. In Schrödinger's original letter, the cat was a protest sign. Take a microscopic trigger that genuinely requires quantum description, say, a radioactive nucleus with a chance to decay in an hour, and tie its outcome to a clear, macroscopic register like a detector, a vial, a relay. If the microscopic piece must be written as both possibilities at once before measurement, then your model of the whole contraption seems forced to carry that structure upward. That sounds absurd because in your everyday world, you never meet half facts. Your coffee is not half sweetened and half unsweetened after you stir. But the point was never to romanticize zombie cats. It was to make you ask whether the quantum state is a physical thing smeared across alternatives or a bookkeeping device that encodes all the ways you might learn about the system. Think of it this way. Before you open a sealed envelope, you can write down your best description of the card inside, and that description includes more than one possibility. You wouldn't conclude the card is literally in several suits at once. You'd say your knowledge is. In quantum physics, the twist is that your uncertainty isn't just ignorance about a hidden, already chosen card. Instead, the theory tells you to use complex amplitudes that can interfere and give different consequences depending on what you choose to measure. The cat was designed to yank that abstract feature into your face. If the math that guides your predictions really lives in superpositions, and if you glue the math to something big, what do you say is real before you look? The modern resolution begins not with mysticism, but with bookkeeping plus a physical process called decoherence. The detector, the table, the air, your skin. All of it is an environment that constantly jostles, scratches, and copies tiny fragments of what happens in the box. Those countless interactions don't collapse the state by magic. They spread information about certain stable properties into the surroundings so quickly that alternatives no longer interfere in any practical sense. It's like trying to unring a bell in a crowded hall. The pattern of vibrations that would let you recombine possibilities into a single, clean tone is shredded as thousands of ears and walls carry different pieces of the sound away. In the cat setup, the alive branch and dead branch get written into different microscopic traces that leak everywhere. Photons scattered off the fur, phonons in the table, electrons in the detector's circuits. Those traces act like the world's messy ledger. You can follow either branch forward and find a consistent story, but you cannot make them meet and cancel, as you can with carefully shielded photons. This explains why you never see giant, fuzzy mixtures of outcomes, even though the equations refuse to privilege one until a record exists. The environment chooses what's robust, so-called pointer states, such as a definite detector click, and rapidly suppresses the interference between alternatives. Collapse, in the sense you experience, is your late arrival to a party where the environment has already posted the result on every notice board. When you open the box, you are not causing the universe to decide, but reading a record it disseminated everywhere. If you want an image that doesn't lie to you, swap the cat for a chain of witnesses. A tiny quantum nucleus faces multiple futures. The detector couples to it and gains a mark in one of two stable configurations. The relay magnifies that mark. The apparatus casing and the air grab a copy. The room picks it up. Your eye makes yet another. Each link is a controlled copy of a particular kind of information. Definite positions of a pointer, definite on-off states, not arbitrary superpositions. Because copying is sloppy and rapid, the only features that survive are the ones that tolerate being copied across millions of degrees of freedom, which is why macroscopic either-ors settle so fast. You don't need secret waves of consciousness or benevolent cats. You need to accept that the world keeps receipts in its environment, and those receipts make classical outcomes durable long before your glance arrives. This picture also clarifies a common confusion. Is the cat really both alive and dead? Wrong question. The quantum state is your best predictive model of the whole entangled setup. It contains amplitudes for different macroscopic records that will not interfere because they have fanned out into uncountable environmental imprints. Inside one branch, there is a cat you'd call alive and a coherent story explaining it. Inside the other, dead and likewise coherent. But you, like any local observer, are embedded in one branch's web of records, and because you cannot erase the environment, you cannot make the alternatives meet. That's not a loophole. It's the practical way the quantum world keeps you from witnessing contradictions. If you're wondering whether this is just philosophy dressed up, notice how laboratories now create cat states of light and electrical circuits on purpose. In optical cavities, experimenters superpose distinct states of a field and show interference when they keep the environment quiet. In superconducting chips, they build microwave resonators that hold two distinguishable patterns at once and then deliberately couple or decouple them from their surroundings to toggle whether interference is visible. The lesson is precise. When you isolate, you can preserve delicate alternatives and make them talk to each other. When you let the world eavesdrop, those alternatives turn into exclusive, classical-looking stories, each with a trail of copies that makes it real for an observer embedded in them. Schrödinger's provocation still matters, but not because it asks you to pity a mythical animal. It matters because it trains your intuition to separate three layers that everyday language muddles. First, there is the model you use to assign possibilities and predict consequences. The quantum state lives here. Second, there is the process by which specific, stable records get written into the environment so thoroughly that interference is gone for good. Decoherence lives here. Third, there is your experience of reading one of those records as the outcome and rationally updating your model in light of it. That update is what people casually call collapse. When you keep the layers distinct, the puzzle unclenches. Superposition is not a fairy tale about undead pets. Measurement is not a wand wave. And reality, at human scales, is the ecology of records that survive copying. You don't have to pick an interpretation today to act on this. Whether you prefer to say there are many coexisting branches you never reconverge with, or that the quantum state is simply your information about a world that yields definite records. The operational advice is the same. Ask what can be isolated, what inevitably leaks, where the records sit, and how quickly the environment writes them. As you do, the box ceases to be a stage for paradox and becomes a tutorial in how the microscopic rules and the macroscopic facts coexist without drama. The math tells you how possibilities flow. The environment decides which properties stick, and you, opening the lid, join a story that was already printed in the air around you. EPR letters. What bugged Einstein? Precisely. You've heard the phrase spooky, action at a distance, but the spookiness wasn't a punchline for Einstein. It was a red flag attached to a precise worry about how a good physical theory should behave when objects are far, apart and out of causal contact. So let's slip into his mindset and read the 1935 EPR argument the way he intended, as a clean, almost courtroom-like test of two principles he cared about: locality and completeness, using a pair of particles that once interacted and then flew so far apart that light could not carry a message between them in time for one measurement to affect the other. Start with the scene he imagined. Two systems created together so that certain properties are perfectly correlated. Think of two coins enchanted, so that if one lands heads, the other must land heads. And if one lands tails, the other must land tails, every time. The quantum version uses more subtle properties than coins, but the flavor is the same. Then send those systems to distant labs, call them A and B, and let two experimenters choose what they measure. The EPR paper proposes a simple criterion for what counts as real. If you can predict with certainty the value of a physical quantity for system B by performing a measurement on A, without disturbing B in any way, then that quantity for B corresponds to an element of reality. Next, apply the second principle. Locality, understood in plain terms, as no influence faster than light. If measuring A cannot possibly disturb B, yet the result at A lets you predict a definite outcome for B, then B must have possessed that definite value all along. Now the trick, in quantum mechanics you can set up the joint state so that you can predict different kinds of quantities with certainty depending on what you chose to measure at A. Choose one setting and you can predict B's position-like property. Choose a complementary setting and you can instead predict B's momentum-like property, each with perfect accuracy, even though the two properties are the sort of pair that quantum theory insists cannot both be sharp at once. EPR's punchline is not gotcha, quantum mechanics is wrong, but this. Given locality and their reality criterion, B seems to carry pre-existing values for both kinds of quantities at the same time, while the quantum state assigned to B alone does not attribute such joint definiteness. Therefore, they concluded, the quantum description is incomplete. It does not list all the elements of reality. Einstein later phrased the worry even more crisply in letters. The wave function for the distant system cannot be a complete description, because what you say about B depends on what someone freely chooses to measure on A, and that dependence should not exist for a thing that is spatially separated and untouched. Notice the careful architecture of the argument. It's not an appeal to common sense or a complaint about strangeness. It's a fork in the road. Either accept that the wave function is incomplete and add hidden variables that assign those definite values, or give up on the locality assumption and allow that the choice and outcome at A can non-locally affect, or at least non-locally correlate with the outcome at B in a way no ordinary signal can explain. Bohr's reply tried to dissolve the force of the EPR criterion, arguing that the meaning of a property is inseparable from the experimental arrangement used to define it. So, without disturbing B is subtler than it sounds. Einstein wasn't satisfied, because to him, the heart of physics was separability. The idea that what exists here should not instantly depend on what someone chooses there. To feel what bugged him, imagine sealing your diary and shipping a perfect copy to a friend across the ocean. If they choose to read the last page, you instantly learn what your last page says, but only because it was printed that way at the start. No mystery. EPR says quantum mechanics seems to create a stronger situation. Depending on what your friend decides to read, different pages of your own diary become perfectly knowable, and the theory, as written, says nothing about those pages until the choice is made. If the book in your hands was truly complete, it shouldn't need someone else's reading choice to tell it what it contains. For decades, that was the impasse. One side stressing locality and pre-existing properties, the other stressing the context of measurement and the sufficiency of the quantum state as a catalogue of predictions. The next chapter, crucial for you to grasp Einstein's lasting influence, came with John Bell, who turned EPR's philosophical fork into a quantitative test. If the world obeys locality and those hidden pre-existing values exist, then certain patterns in the joint outcomes must obey an inequality. Quantum theory predicts and the laboratory observes violations of that ceiling. Modern experiments, using entangled photons, trapped ions, superconducting qubits, even starlight to choose settings, repeatedly find those violations, while carefully blocking ordinary channels of communication, which means local hidden variable completions of the EPR kind do not work. But notice what this does and does not say. It does not permit faster than light messaging. It says that any underlying story must either allow non-local correlations that defy a classical bookkeeping of pre-existing values, or it must abandon the idea that measurement choices are independent of the hidden variables. or it must reinterpret what the quantum state represents. In other words, Einstein was wrong in the direction of the fix, but right about the pressure point. Entanglement forces you to rethink how separate systems share a joint description. If you keep your head clear, the lesson is balanced and practical. EPR's argument taught physicists to state their assumptions plainly, to separate what you can predict from what must already exist, and to design experiments that trap theories in contradictions if they try to preserve certain classical intuitions. For you as a learner, the payoff is a cleaner map of the conceptual terrain. Locality is not the same as no correlations. It is a constraint on influences. Completeness is not predict everything. It is list all there is to be listed. Elements of reality are not things you like. They are quantities you can predict with certainty without touching the system. On this map, entanglement is not a ghostly wire between distant objects. It is a rulebook for how joint predictions outperform any story that assigns separate, prefixed values to each side. And the calm closing truth, the one Einstein helped carve even as he resisted it, is that the quantum world lets distant systems share a coordinated script that no local rehearsal can imitate. A script you cannot use to send a message faster than light, yet one that refuses to be explained by properties each actor carried alone. The paper intended as a complaint became the blueprint for the most precise experiments we have, reminding you that in physics, irritation at a theory's oddities is often the first step toward discovering just how tightly reality holds its secrets together. Wigner's friend, multilayer and interactive you, walk past a closed lab and realize the strangest thing about it isn't the sealed door, it's the idea that two perfectly rational scientists might give two perfectly correct but mutually incompatible descriptions of what's happening inside. So let's set the stage the way Wigner imagined, and then push it into a multi-layer, interactive maze that shows you where the real pressure points live. Inside the room, your colleague, the friend, measures a single quantum system and writes the result into a notebook, a definite record by their own lights. Outside, you model the whole lab as a single, delicate system that could still, in principle, show interference if you performed the right gentle test, because you haven't peeked and you've treated the room as a well-isolated black box. Already you can feel the tension. The friend says, "I saw a result." You say, "The joint lab might still be in a superposition." And neither statement is sloppy if you keep track of who has access to what information. Now make it multi-layer. Add a super friend who watches you, or chain two sealed labs that later interact, or even split the choice of what to test into two distant wings, so that the decision to probe for interference or to ask for the written result can be made independently. These stacked versions turn a philosophical itch into structured experiments that ask whether quantum rules apply to observers themselves and whether all observers can consistently treat outcomes as single facts that everyone can agree on later. The interactive twist is crucial. If the outside observer wants to reveal interference, they must ensure the friend's record hasn't leaked into the environment. Even a tiny trace, light scattered off the notebook, heat in the air, acts like a broadcast, making the alternatives distinguishable and destroying interference. If, instead, the outside observer opens the door and asks, "What did you see?" the very act of comparing notes commits the world to one branch-like story and shuts down the possibility of observing interference afterward. This isn't mysticism, it's bookkeeping about records. To keep the door closed and test for interference, you must erase any which result information the friends stored, which is only feasible when that information is encoded in a reversible microscopic form, say, a controlled atom or few photons, not in a human brain and pencil marks. That is why laboratory demonstrations use tiny friends, quantum memories and light pulses, implementing the logic of the paradox without pretending that consciousness is special or needed. Push one step further and you meet modern no-go results tailored to these scenarios. One line of argument shows that if you demand all of the following at once, quantum theory gives correct predictions for all systems, including observers. Each measurement leaves a single definite outcome for any observer who performs it. Different observers' inferences about events can be pooled into a single global story without contradiction. Then nested Wigner friend setups lead you into logical dead ends. Another line translates the tension into testable bounds. If you assume locality plus observer-independent single outcomes plus quantum correctness, then certain combinations of correlations should never be seen. Small-scale photonic experiments violate those bounds, telling you that at least one cherished assumption must give way. None of this licenses faster-than-light messages or magic mind power. It says your picture of facts must be more carefully framed than the classical picture suggests. So what can give? One route lets the universal quantum description stand untouched. The friends I saw outcome A is correct within a branch that includes their notebook and memories, while the outside observer is also correct to model the closed lab as capable of interference relative to their information. When they meet, their stories synchronize, and there's no contradiction because the meeting itself is a physical event that selects a consistent record. Another route says facts are always about relations. The pointer reads A for friend relative to friend, while the lab shows interference relative to Wigner until interaction, and trying to paste these into a single, observer-free ledger is a category error. A third route treats the quantum state as a user's betting guide. The friend updates on the observed result, the outside observer updates on a different data set, and only upon exchanging messages do they align their odds. There's no hidden contradiction because states were never global properties. A different path modifies the rules at the macroscopic scale, suggesting that beyond some threshold genuine collapses occur that prevent large superpositions. This is actively probed by experiments that try to maintain interference while gradually increasing the size and complexity of the friend. With multilayer versions, you learn something operational. Interference demands silence, no leaks, no copied records, while agreement of stories demands interaction. Open the door, swap messages, let the world align. You can't have both simultaneously, so every design is a choice about which question you're asking. The interactive angle makes this vivid. You can engineer a device to sometimes treat the Friends Lab as a closed system, and other times open it, even choose between these options at the last instant. But you won't catch the universe contradicting itself because each option routes the information flow along a different path that protects consistency. What these thought experiments and their small-scale realizations do is teach you discipline. Say who knows what. Say when information is copied, and say whether you are testing for sameness of stories or for the ghost of alternatives that only show up when no record has been made. The reward is a clearer view of what Wigner's question was really about. Not whether minds cause outcomes, but whether the rules that let you speak about measurements can be applied recursively to the measurers without tearing the fabric of explanation. The sober answer is yes, provided you loosen at least one classical habit, such as a single observer-independent catalogue of facts, or the idea that outcomes exist for everyone before information has flowed. And the gentle closing thought, the one you can carry past the sealed door and into your own life, is that understanding grows when you track the routes that information takes. When to preserve possibilities by shielding a system, when to trade possibilities for clarity by letting records spread, and how to treat another person's knowledge as a real, physical thing that only becomes part of your world when you make contact. Two views, each complete on its own terms, harmonizing the moment the door finally opens. Quantum suicide and probability puzzles. You've probably heard the daring claim that if reality constantly splits into alternatives, then some version of you survives every lethal gamble and, from your own point of view, you're almost guaranteed to feel immortal. But that slogan is a trap built from loose words about probability, identity, and evidence, so let's slow the scene down until each moving part becomes clear and you can see why the so-called quantum suicide argument isn't a physics ticket to eternal life, but a tangle of probability puzzles that teaches you how to reason more cleanly about chance in a branching world. Begin with the apparatus, not the mythology. Imagine a perfectly isolated quantum device that sometimes fires and sometimes doesn't, coupled to a mechanism that would be fatal if it fires. Under a many branches picture, both outcomes occur in distinct, non-interacting records, each with a weight set by the squared amplitudes that the lab's math assigns, the Born rule. Proponents say, Because there is always at least one branch in which the device doesn't fire, there is always a future you who lives to tell the tale. And since a dead observer never reports their demise, your first-person experience will slide along the living branches forever. That line feels persuasive until you examine the words you, guarantee, and experience. In actual quantum experiments, the frequencies you and your colleagues record match the Born weights to high precision. That is, typical observers in repeated trials see the statistical law, not miracle runs. And the reason is not censorship by fate, but the way records multiply in proportion to those weights. If you run the lethal device once, there will indeed be a thin sliver of branches where you live. If you run it many times, the measure, the total weight of branches where you're still alive, shrinks rapidly, even though a bare count of branches might still be infinite. Probability in quantum theory is not a naive branch census, it's weighted typicality. That single idea dissolves the first illusion. Saying, some branch contains me alive, does not license the expectation I should anticipate survival, because rational anticipation should track weight, not mere existence. Put differently, future observer moments come in differing abundance, and the theory tells you which ones are plentiful. A rule for personal expectation that ignores abundance is not brave, it's incoherent. The second illusion hides in the word you. Personal identity is not a flashing dot that hops between realities. It's an ongoing pattern embedded in a web of records, brain states, lab notes, shared memories, maintained by physical continuity. In a branching process, countless near copies of that pattern continue. But what makes them you is not a mystical thread. It's their structural match to your present information. When you risk annihilation, you are not choosing which copy to become. You are choosing the distribution of future copies that exist at all. And the overwhelming share of that distribution may contain no you-like pattern if the device fires. That is why appeals to, from your own perspective, you always survive, confuse the narrative you tell after a lucky run with the rational forecast you should make before pressing the button. If you adopt any decision policy that values future experiences in proportion to their born weights, a policy that, in ordinary labs, makes you accurately predict observed frequencies, then quantum suicide scores as disastrously as Russian roulette does in a classical casino. A third knock comes from evidence. Can a survivor ever confirm the guarantee they were promised? No. A single survivor necessarily lives in a selection-biased branch, so their survival provides no discriminating evidence between branching with born weights and no branching but a wildly lucky series of outcomes. Meanwhile, colleagues in the far more abundant branches, where the device fired early, cannot report anything, so the thought experiment fails a basic scientific test. It generates no publicly shareable confirmation that the risky policy achieved anything beyond reckless filtering of observer moments. This is not a quirk of interpretation. It follows from the fact that branches cannot signal to one another, and that conditioning on being alive skews any naive inference you make from your own case. A fourth lesson comes from ethics and utility. If you care about your future experiences at all, you implicitly care about how much of that future there is, not merely whether at least one sliver remains. Utility functions that ignore measure reward behavior that predictably erases almost all continuations of your life, which clashes with every ordinary preference you have. Keeping promises, avoiding grief you inflict on others, preserving projects that require more than a razor-thin set of branches to succeed. Decision theory programs that derive the born rule from rational preferences by insisting on coherence across hypothetical bets or on symmetries in how information can be rearranged do not aim to please philosophers. They explain why agents who want to avoid sure loss strategies must weight branches by squared amplitude in their planning. Under those norms, the quantum suicide policy is a guaranteed utility sink. It buys a dramatic story in vanishing measure at the price of eliminating almost all of your future value. There is also a practical physics point often glossed over. The idealized gun that couples a clean quantum trigger to a macroscopic outcome without leaking information is a fiction. Real devices spray telltale traces, heat, light, vibrations into the environment, and those traces rapidly lock in the outcome. That doesn't rescue the policy. If anything, it makes it worse. Because once records have spread, there is no reversible trick to recombine possibilities or to switch outcomes. You are not surfing uncertainty, but carving permanent disjoint histories, most of which end your story. And here is a quieter, final puzzle for your intuition. Suppose someone tried to replace physical risk with pure copying, cloning you 1,000,000 times and rewarding a few copies lavishly while erasing the rest. Even in a non-quantum scenario, most future yous do not enjoy the reward. Any expectation rule that tells you to expect becoming one of the few winners simply because winners exist would also tell you to play lotteries where 99% of your continuations starve. The wrongness you feel there is the same wrongness inside the immortality slogan. It confuses existence with expectation and treats self-locating uncertainty as a cheat code. The calm way out is to keep 3 rails under your reasoning. First, separate public frequencies from first-person anecdotes. Physics speaks through patterns seen by many observers, not stories preserved by the luckiest survivors. Second, weight futures by the abundance that the theory itself prescribes. If you want your everyday laboratory bets to be right, you must carry the same rule into dramatic choices. Third, refuse to treat murderous filters as epistemic upgrades. No experiment that silences dissenting branches can teach you more than you could have learned by safe, repeatable tests. In that light, the quantum suicide tale no longer dangles a promise. It offers a mirror. It shows how easily the human mind slides from "there will be a surviving branch" to "I should plan as if I were guaranteed to be that survivor." And it invites you to repair that slide by anchoring identity in records, probability in weights, and evidence in shareable patterns. Do that and the morbid glamour evaporates. You are left with a sober rule for living in a branching universe. Opt for policies that preserve and thicken the measure of futures in which you and those you care about continue. Because in quantum mechanics, as in life, what you should expect tomorrow depends not on whether a story exists, but on how much of the tomorrow there will actually be. Delayed choice with cosmic beacons. You might think that deciding how to look at a particle after it has already flown past the crucial fork in an interferometer is like choosing the end of a story after the last chapter has been printed. But delayed choice experiments, especially the ones that use light from ancient quasars as cosmic beacons, teach a subtler lesson. In quantum physics, what your apparatus can meaningfully say about a particle depends on the entire measurement context you actually build. Even if that context is arranged at the last possible moment, and pushing the choice back to signals emitted billions of years ago only strengthens the point without inviting time travel or fairy dust. Picture the playground. A single photon approaches a Mach-Zehnder interferometer, a device with 2 paths and, optionally, a final beam splitter that recombines them. If that recombiner is in place, the apparatus is tuned to reveal interference, a wave-like pattern that depends on the relative length of the 2 roots. If the recombiner is absent, the apparatus is tuned to reveal which path information, particle-like behavior with no interference. Wheeler's question was almost mischievous in its clarity. What if you decide whether to insert or remove that final element after the photon has already chosen its route? Classical storytelling wants to know which tale is true. The photon went this way, or the photon went both ways. And delayed choice seems to dare the universe to pick a genre after the scenes were filmed. But when you actually run the experiment with honest timing, so the decision happens so late that no ordinary influence can carry news back to the earlier fork, you don't catch the universe revising the past. You catch your own expectations changing. With the recombiner present, you always see the interference pattern appropriate to a setup that erases path distinctions. With it absent, you always see singles that match a setup that distinguishes paths. The results are exactly those predicted by quantum theory, which never promised pre-written path facts. It promised probabilities that belong to the arrangement you realized. Now for the cosmic upgrade. Skeptics of such tests often appeal to a freedom of choice loophole. What if the hidden variables that supposedly carry pre-existing properties somehow nudge your random number generator so that your late choice was never really free of the particles past. Enter the sky. In cosmic delayed choice and related cosmic bell experiments, researchers aim telescopes at quasars or stars separated on the sky by vast angles and use the arriving starlight, its color or arrival time, to set the detector configurations in real time. Because those photons began their journey billions of years ago, any conspiracy that arranged your local choice to be secretly correlated with the particles' hidden settings would have to be written into the universe before life on Earth, before the sun formed, sometimes before our galaxy settled into its modern shape. The method is simple in spirit. Treat the cosmos as a gigantic, ancient randomizer and route its flickers into fast electronics that switch your interferometer or your polarizers on the fly. When you do this carefully, ensuring that the switching occurs so quickly that no signal slower than light can coordinate the particle's behavior with your choice, you see the same quantum signatures as always. Interference when you recombine, which path patterns when you don't, and in the Bell-style versions, correlations that violate the bounds any local, pre-assigned properties would obey. The philosophical pressure changes tone once you grasp this. The point is not the future affects the past, because no information-bearing influence outruns light. No one transmits a message into yesterday, and you cannot use delayed choice to send a signal to your former self. Instead, the point is that the kinds of statements you're entitled to make about what the particle did are inseparable from the measurement context, which includes your late choice. The particle never carried a little diary that listed both which path and how the waves add for you to read at will. Complementarity was always a rule about mutually exclusive questions, and delayed choice experiments, cosmic or otherwise, dramatize the rule by letting the question be finalized after the system has entered the stage. If that still feels like retrocausality, examine the causal arrows more carefully. The distribution of outcomes in each run depends on the setting you implement, but there is no run in which the particle gives both an interference signature and a which path tag. You can retrodict, given the observed clicks, which setup must have been realized, yet you cannot force an earlier event to rewrite itself. In the data, what changes is the pattern collected under one or the other context, not a single event viewed two ways. The cosmic beacons simply make it ludicrous to imagine a local hidden script coordinating both the particle and your setting generator in the last instant. They push any such script to the deep past, where it becomes less an explanation and more a superstition. Everything was rigged from the beginning, and science has a name for that move: unfalsifiable. What you gain instead is a practical discipline for thinking about experiments. First, decide what question you're asking. Do you want interference? A story about phase relationships across paths? Or which path? A story about localized histories? Second, design the apparatus so the environment does not leak the unwanted information. Interference is delicate. It dies if the world picks up path clues, so your optics must prevent accidental scattering that would mark the routes. Third, choose your settings in a way that severs easy causal links to the particle source. Fast electronics and astronomical randomizers serve this goal. When these conditions are met, the outcomes are crisp and repeatable, and the lesson holds across scales and technologies. Single photons in fiber loops, atoms in interferometers, superconducting circuits engineered to mimic the logic, all obey the same contextual bookkeeping. The softer payoff, the one that helps you think more clearly beyond the lab, is recognizing that a fact isn't a naked property that exists independently of the questions asked about it. It is a stable record produced by a specific interaction chain. In everyday life, that chain is so robust you can forget it's there. In a delayed choice experiment, you bring the chain into focus by deciding late, loudly, and from far away what the chain will be. The calm closing thought is that this isn't an invitation to magical thinking, but to intellectual honesty. The universe does not bend to your whim, nor does it repaint its past to suit your mood. Rather, it refuses to let you speak simultaneously with authority about answers that belong to incompatible questions. Cosmic beacons help you see that refusal in sharp relief. Ancient light flickers. You flip a switch, The apparatus answers the question you actually asked, and the past remains what it always was. A reservoir of potential stories that only become definite in the context you truly build. Not the one you daydreamed about after the photon had already flown. Many worlds betting and decision theory. Imagine standing at a casino doorway where every quantum toss will not pick a single future, but will split your storyline into parallel continuations. And the bouncer says, you may still place odds and buy insurance. So what counts as a fair bet when tomorrow will contain many versions of you reading many different outcomes? That question is the heart of many worlds' decision theory, and answering it cleanly teaches you how to think about chance, value, and rationality when outcomes multiply instead of exclude one another. Begin with the practical problem, not metaphysics. Before a measurement, you can sign contracts, wages, insurance policies, side deals that will pay different amounts to your future branch descendants depending on what the lab shows. After the measurement, those contracts are delivered to the corresponding copies, and none of those copies can trade across branches because the records are sealed into separate histories. The puzzle is to set your terms today so that taken as a whole across all the continuations that you care about, you are not leaving guaranteed money on the table. A first temptation is branch counting. If a measurement yields 3 recorded outcomes, split your stakes equally. But branch counting has no stable meaning, because how you declare a branch depends on arbitrary modeling choices. How finely you describe the environment, where you draw the line between microscopic differences, what you coarse grain as the same. The lab's dynamics preserve something objective instead. The squared amplitudes associated with outcome records, which behave like a conserved budget that cannot be reshuffled by simply redrawing the diagram. A second temptation is reckless favoritism. Declare that you only care about the single future copy that sees the biggest payout and ignore the rest. That policy looks bold, but fails an elementary sanity test. A bookie can then offer you a sequence of trades that each look locally attractive, yet leave every future copy worse off than an alternative package you could have accepted, a kind of guaranteed loss spread across your descendants. To avoid these traps, decision theorists frame a small set of common sense requirements and watch where they point. First, if one option yields at least as much for every future copy and strictly more for some, prefer it. This is dominance. Second, do not change your ranking if an outcome splits into subcases that do not alter the totals delivered to those subcases. This is branching indifference, and it reflects the fact that duplicating a record without changing what that record receives should not by itself sway you. Third, keep promises to your future selves in the mild sense that a plan you judge best today should still look coherent to the copies who inherit it tomorrow. Otherwise, a sequence of your own updates can be strung into a cycle that extracts value from you for free, which is the many worlds version of a Dutch book. From these minimal commitments, plus the symmetry that relabeling equally prepared outcomes should not matter, you are driven to weight outcomes in proportion to their squared amplitudes when comparing packages of payoffs. This is not mysticism. It is the only weighting that remains stable under the kinds of splits that unitary quantum dynamics inevitably produce. And it is the only one that prevents clever contracts from draining value across your lineage. To see the force of the rule, picture an Everettian insurance market. Before a measurement with 2 recorded outcomes, call them low and high, you may buy a policy that transfers a bit of value from the high branch to the low one, evening things out so that no future you feels ruined. If you price that transfer by squared amplitude weights, no arbitrage appears. An insurer cannot untangle your policy into a portfolio that makes every future copy of you envious of what you could have had instead. But if you price by branch count or by your favorite branch alone, the insurer can assemble a package that exploits the mismatch between how value moves through the branching and how you perceive it, leaving your collective future strictly worse. In this setting, squared amplitude weights play the same role that probabilities play in a single world lottery. They are exchange rates that keep rational preferences consistent when nature offers uncertainty. What about the feeling that I will wake up as one particular copy, so why should I care about the rest? The many worlds answer is not theological, it is practical. Before the split, you face self-locating uncertainty. There will be several continuations, and, from the inside, you do not yet know which notebook you will later read. A reasonable attitude is to treat each continuation as a future center of experience that you own some responsibility toward, and to apportion that responsibility by the same structure that governs how often those centers appear in successful retrodictions of lab frequencies, namely squared amplitudes. Ethically, this is akin to planning for your children in the plural. You do not know which future needs will be most urgent, so you spread resources in a way that tracks how those futures are expected to unfold. Notice how this view reshapes risk. Classical risk pits, mutually exclusive outcomes against one another. In a branching world, you are balancing the welfare of a family of successors who will all exist. A purely risk-seeking policy that chases spectacular jackpots for a tiny slice of descendants, while impoverishing the vast majority, is not daring, it is neglectful. Conversely, a purely risk-averse policy that equalizes everything at great cost can waste opportunities. Many worlds decision theory therefore mirrors ordinary prudence. Choose the trade-offs you would endorse if you could simultaneously sit in all the chairs that your descendants will occupy, and let the amplitude weights tell you how many chairs of each kind will be filled. This is why long-run calibration matters. In repeated experiments, the frequencies reported by almost all branches match the amplitude weights, and agents who price bets with those weights make forecasts that their future selves judge accurate. Agents who price by branch count or by wishful favoritism will, in the futures where they still have resources to reflect, see a record of systematically bad deals they accepted. The lesson is not merely about gambling. It reaches into how you structure research programs, investments, and safety margins. In a world where small quantum events seed big differences, think of error correcting, protocols that allocate resources across many likely fault patterns rather than preparing for a single dramatic one. Finally, this framework helps you tidy the language you use around chance. In many worlds, there is no single role that could have gone otherwise, and then did not. There is a family of recorded roles, each with a share of the total. The role of a probability rule is to guide choices in the face of this family, so that your cross-branch legacy is the one you meant to leave. You can still be adventurous, still fund long-shot projects, still buy tickets to uncertain rewards. You simply price them by the same weights that keep your collective future from bleeding value through avoidable incoherence. And the soft closing truth, the one that replaces anxiety with craft, is that betting in a branching universe is not about predicting a unique fate. It is about designing a portfolio of fates you can endorse, knowing that each future you will open the ledger and see that, by the only exchange rates that resist exploitation, you treated them fairly. Quantum Russian roulette ethics. Picture a dare dressed up as philosophy. Someone claims that if the universe constantly branches, then staging a version of Russian roulette with a quantum trigger is ethically no worse than flipping a harmless coin, because some copy of me always survives, and since only survivors can complain, the stunt leaves no one to mourn. But ethics begins exactly where that sales pitch ends, by accounting for duties to others, for responsibilities across uncertain futures, and for the quiet ways selection bias can launder harm. So let's slow the argument until its moving parts become visible and your moral compass can work. Start with consent and scope. Any act that can end a life radiates beyond the chooser's thrill, touching families, partners, colleagues, rescuers, emergency systems, and the broader community that bears the shockwaves of loss. These people do not live only in branches where you survive, and their suffering is not erased by your inability to hear from branches where you died. Ethics counts harms whether or not a witness remains to file a report, a policy that makes grief and obligations most abundant in the very futures where critics cannot speak is not clever. It is exploitative. Next, consider responsibility across branches. Many worlds talk tempts you to treat each outcome as a separate world where you owe nothing to lost versions of yourself. But planning happens before the split, when you still stand at the hub of all continuations. And from that vantage, you can choose policies that either preserve a rich forest of lives or prune most of them away. Morality cares about the totality you foresee causing, not just the slice that later sends you postcards. If you value promises kept, projects sustained, and people depending on you, then amplifying a thin line of lucky continuations while predictably extinguishing most others is a failure of stewardship, not an act of courage. Now turn to the ethics of evidence. A stunt that silences the largest group of those affected cannot honestly be used to argue its own safety. Survivor testimony is the most biased dataset imaginable, and designing an experiment whose negative outcomes cannot be reported is the moral mirror of stacking a jury. In science, we require results to be shareable and repeatable by many observers. An experiment that destroys most observers is not just bad methodology, it violates the duty to pursue knowledge without instrumentalizing people as disposable filters. Bring in risk externalization. Even if a device is perfectly isolated in theory, in practice, it leaks heat, noise, and mechanical strain into an environment that others inhabit. Misfires and near misses impose costs on healthcare, on responders, on those who discover the aftermath, and on institutions that must set rules to prevent copycat attempts. By rebranding a lethal hazard as a metaphysical demonstration, the would-be gambler shifts burdens onto strangers who never agreed to participate, violating the basic norm against making others carry your private risk. Consider also integrity and moral hazard. A community that tolerates quantum excuses for reckless endangerment invites a market for rationalizations. If my preferred worldview makes me unkillable, from my point of view, why not take any bet that thrills me? The answer, ethically, is that a shared world cannot be governed by first-person slogans. It must be governed by rules that strangers could accept without knowing which role they will occupy in the story. That is the spirit behind universalization tests in moral philosophy. Imagine a world where people routinely adopt a policy of selecting for spectacular survival stories by eliminating most continuations. The result is a society with fewer reliable caregivers, more abandoned obligations, and a degraded trust that others will act to preserve the overlapping futures we share. Even strictly consequentialist views warn against such policies, not only because they expect more suffering overall, but because they destroy the stable expectations on which cooperation depends. Then there is autonomy and informed consent. To stage the stunt, you need space, tools, and often the forbearance of others. Yet no bystander can truly give informed consent to a plan whose negative outcomes include their own trauma, the reallocation of community resources, or the burden of explaining your choices to children. Ethical review boards exist in research precisely to block experiments with catastrophic downside for subjects and bystanders. Quantum does not grant an exemption from the principles of minimizing harm, maximizing social value, and respecting persons. Move to personhood and dignity. Treating your future selves as chips to be erased if they fall on the wrong side of a measurement ignores the moral weight of continuity. Memories, relationships, and projects that give your identity substance. If you grant that these patterns matter, then you owe those patterns care across all the plausible futures you can still influence. You do not get to rename annihilation as branch selection and claim the ledger is balanced because a single narrative of you remains. The same logic extends to others. When someone loves you, they do not love only the luckiest continuation. They love the living, changing pattern across ordinary days. And you breach that relationship when you knowingly choose a plan that removes almost all versions of you from their world. The argument also collapses under its own epistemic weight. Because branches cannot talk, the stunt can never confirm its premise to the survivor. Any surviving, you cannot rule out that they simply got lucky in a one-world universe, while the far more numerous worlds where you died provide no testimony. A moral policy that cannot, even in principle, be audited for its claimed benefits, but guarantees irreversible harms, is precisely the sort of policy we are obliged to reject. And if you try to dodge ethics by shrinking the stunt to a pure thought experiment, that dodge backfires. Once the fantasy loses contact with actionable evidence, it stops being a guide to living agents and becomes a caricature of choice, useful only for revealing our appetite for self-serving narratives. Finally, restore realism to the physics without sliding back into equations. Real devices are noisy. Outcomes, once recorded in the environment, do not recombine. There is no graceful undo button that rescues the branches you've cut. Taking those facts seriously is already a moral step, because it forces you to account for the permanence of harm instead of hiding behind the romance of multiple worlds. So the ethical verdict is not a scold, but a calm recentering. In a universe that may well branch, responsibility does not thin out, it thickens. To act well is to plan for many futures, to avoid policies that predictably erase most of the people they affect, and to measure success by what is shareable, survivable, and decent for those who do not get to be the hero of the story. If you want an ethically adventurous life, there are better frontiers. Build safer experiments that stretch knowledge without selecting survivors. Design protocols that reduce risk for everyone who will inherit your choices. And cultivate a courage that counts not the single dramatic tale that remains, but the broad, quiet flourishing of as many tomorrows as you can keep alive. Twin boxes and the three-box paradox. Open two identical boxes in your mind and place a single, well-prepared quantum particle somewhere you won't peek yet. Now add a third, and promise yourself you'll only open one box in the middle and one different box at the end. The twin boxes warm-up lets you feel how interference reshapes simple either-or stories. And the full three-box paradox shows how carefully chosen preparation and final filtering can make it seem, sentence by sentence, as if the same particle was certainly in two different places, even though nothing supernatural is happening, and no honest experiment ever sees two copies at once. Start gently. With two boxes, you can wire the paths so that if you later choose a recombining measurement, the device reveals an interference outcome that depends on phase, while if you choose a straight witchbox measurement, you get ordinary exclusivity. One box clicks, the other stays silent. The catch is that you must decide which question you'll ask, because the setup that shows interference is not the setup that reveals a trail. Once you've seen this with twin boxes, you're ready for the move that makes the three-box story famous. Pre-selection and post-selection. Pre-selection means you prepare the particle. In a definite starting arrangement, think of it as quietly, spreading its chance of being found across all three boxes in a controlled way, while post-selection means you commit at the very end to only keeping those runs in which a specially chosen final test clicks. The magic-looking claims arise when you insert a brief, honest question in the middle. If I had opened box A right now, would I have found the particle? And then separately, in a different run with otherwise identical timing, if I had opened box B right now, would I have found the particle? With the right bookends, the right beginning and end filters, the statistics answer yes to both counterfactuals. In the subset of trials you keep, opening a midstream would have found the particle with certainty, and opening B midstream would also have found it with certainty. Read sloppily, that sounds like two places at once. Read carefully, it says something subtler about conditions and contexts. You never perform both mid-course checks in the same run, and the guaranteed yes is conditional on the final filter succeeding, which itself depends on not disturbing the setup in a way that would block that success. The paradox earns its name because classical common sense expects the two, if I had looked there, guarantees to add up to double occupancy, while the kept data still adds up to one particle overall. How can that be? The practical answer lives in how the final test sifts your data. The post-selection step discards most runs and only admits those where the particle's hidden phase relations conspire to make both hypothetical checks come out favorably, each considered in isolation. If you actually open both A and B mid-run together, you ruin the very interference that the end filter relies on, and the certainty evaporates. Experiments make this precise without symbols. With single photons, each box becomes a branch of an interferometer, and the middle query is a gentle marker. Say, a tiny device that would soak up a trace of light if the photon were in that branch. When you put the marker in one path only, and keep only those trials that later trigger the chosen final detector, you find that the marker in A always registers, and the marker in B also always registers in a separate batch of trials built to ask that other question. even though, across all the kept data, the total energy and count add to just one photon's worth. If you're worried that measuring without disturbing hides a trick, notice that the middle step can be tuned from strong to weak. In that weak regime, the 3-box game yields another eyebrow raiser. The pointer shift looks as if there were one full particle in A, one full particle in B, and a kind of negative presence in C, so that the net still sums to 1 when you add the shifts. This is not wordplay about ghosts. It is a faithful accounting of how a minuscule probe couples to a pre- and post-selected system. The negative contribution means that the trace your probe would normally read in C is anti-correlated with the records you keep, cancelling part of the total in the average. You never catch minus a particle in a single shot. You only see its signature in aggregate and only under the chosen bookends, which is why the effect does not allow signaling or magic duplication. If this still feels like a cheat, try translating the paradox into ordinary conditional language you use every day. Suppose you send out invitations and later decide you will only stay at the party if exactly the right pair of friends arrive. If, mid-planning, you had privately asked either friend A or friend B whether they were coming, you would have gotten a confident yes in each separate hypothetical, because the eventual decision to stay filters for worlds where the plan happens to include each of them when asked alone. Yet you cannot use those two certain answers to claim both were at your party twice. The filter that defines the party you stayed at entangles the conditions. Quantum 3-box experiments formalize this intuition with exquisite timing and optics. The mid-run question and the end-of-run filter are not independent levers, but parts of one measurement context, and statements about where the particle was must be attached to that full context to be meaningful. The educational payoff is twofold. First, you learn to distrust counterfactual reasoning that treats mutually exclusive tests as if they could be combined after the fact. The paradox dissolves when you insist that what would have happened belongs to a specific experimental story with a specific end condition. Second, you discover a practical tool, pre- and post-selection. Plus weak probing lets you map where a system leaves a telltale trace inside a complicated device without crushing the very interference that makes the device work, a method used to debug interferometers, align integrated photonic circuits, and study how information flows through quantum networks. The deeper lesson is philosophical but sober. Quantum statements about being somewhere are not inventory lines in a hidden warehouse. They are claims about how records build up under carefully staged questions and filters. When a setup is tuned so that asking about A or asking about B each aligns with the final filter, both questions earn yes in their own counterfactual worlds. Yet the lab never prints a single ticket that reads 2 particles found. If you carry that discipline back to the simpler twin box case, everyday puzzles lose their sting. Interference devices do not hide tiny doubles. They connect beginnings and ends with rules that your choices help define. And the soft closing thought is this: when a paradox invites you to shout impossible, try whispering, under which conditions? Because in quantum strategy, as in life, the answers you can count on belong to the questions you actually asked and the commitments you were willing to keep all the way to the end. Hardy's setup with real-world twists. If you want to watch quantum logic corner itself without leaning on any inequality, Hardy's setup is the small stage with the sharpest spotlight. And when you add real-world twists, loss, imperfect interference, jittery phases, and human attempts to peak gently, you see why a paradox that fits on a napkin still keeps experimentalists humble and busy. Picture 2. Mach-Zehnder interferometers side by side, each tuned so that a single photon entering one would always end up at its bright detector and never at its dark one. Perfect destructive interference blocks that dark port when the device is balanced. Now let the interferometers overlap in one arm like 2 narrow corridors that cross. In the textbook story, if both particles take their overlapping routes at once, they would bump. In the electron-positron version, they would annihilate, which ruins the delicate phases that normally guarantee the dark ports stay dark. Here's the tease. Hardy shows that there's a non-zero probability that both dark detectors click together, even though each dark click is supposed to be a certificate that the other particle took the overlapping corridor and forced the first one off its interference. Put the certificates side by side and you get a joint claim that should be impossible if each particle locally decides its route without the other's say. No inequalities, no long algebra, just a crisp, this and this cannot both be true under local prefix stories. Yet the lab produces those pairs of dark clicks. In the real world, you don't play with annihilating beams. You build a photonic version that mimics the logic. Single photons enter two interferometers. One arm from each overlaps on a shared beam splitter. And carefully chosen phase shifts make hardy events, joint dark clicks, appear at a small but clear rate when everything is aligned. The first twist is visibility. Those perfect cancellations that create dark ports require the paths to be indistinguishable down to timing, spectrum, polarization, and spatial mode. If even 1 degree of freedom leaks which path hints, interference softens, and your dark port glows faintly for the wrong reasons. That's why experimenters pair their interferometers with heralded single photon sources, so that every trial starts clean, and spend days massaging fiber lengths, compensating dispersion, and matching spectra. So two photons meeting at the shared coupler truly behave like twins. The second twist is stability. The relative phase between arms must hold still within a sliver of a wavelength over thousands or millions of runs, or else what you interpret as paradoxical coincidences are just the average of a wandering instrument. Labs fight this with active feedback, piezo stretchers that nudge path length, and temperature-stabilized platforms that keep drift below a whisper. The third twist is fair sampling. Because hardy events are rare by design, you must make sure your detector misses, and source losses don't cherry-pick a special subset of runs. Otherwise, joint dark clicks could be inflated by selection rather than by the quantum constraint that Hardy uses to corner locality. Modern experiments push detector efficiency high and use heralding to count every trial. Photon announced at the source, registers or it doesn't. So the dataset reflects reality, not wishful pruning. Once the plumbing is honest, what do you actually learn from the clicks? You learn that you cannot keep all three of these together. 1. Each particle carries a root story that exists before the other's choice and is independent of it. 2. The devices act only locally on what enters them. And 3. The specific interference cancellations and dark means overlap inferences that your single device calibration taught you. You can keep any two. The third breaks in the joint experiment. If you save local root stories, you must give up the calibration inference that a dark click certifies. The other took the overlapping corridor. If you save the calibration inferences for each device, you must let go of local root stories, or allow that what's true for one depends on the full joint context. The power of Hardy's setup is how little it assumes. No inequality bookkeeping, no appeal to statistical loopholes, just your own device characterizations coming back to bite when you combine them. And then come the gentler peaks that feel like a cheat code, weak measurements. You can couple a feather-light probe to one arm, so light that a single run tells you almost nothing. But a large average reveals a tiny shift and ask, where did the particle's effective trace lie in the sub-ensemble that produced Hardy events? Map all arms this way and a strange picture emerges. The weak pointer says the particle left a positive trace in each of two arms that classical logic would have forbidden simultaneously, along with a compensating negative trace elsewhere so that the whole map still sums to the single particle you put in. This isn't a ghost report. It's a faithful reflection of how your almost non-invasive probe couples to a pre- and post-selected bunch of runs, the very runs defined by Hardy's paradoxical coincidence. If you crank the probe up to a strong measurement, the paradox evaporates because you've broken the interference that made the inference meaningful. The map is a property of a context, not a hidden itinerary. Real instruments add two more twists that matter if you want truth rather than theatre. First, partial distinguishability. Even a picosecond of timing mismatch can mark the photons enough to suppress the shared coupler meeting that Hardy relies on. Labs use spectral filters and delay lines to erase that telltale offset. And they test the erasure by checking Hongu-Mandel dips. The depth of that dip is a witness to indistinguishability and a predictor of how clean your hardy data will be. Second, crosstalk and stray reflections. In tabletop optics, invisible back reflections can route a whisper of light to the dark port, independent of the paradox. So researchers add optical isolators, angled facets, and beam dumps, then perform control runs, misalign the shared coupler on purpose, or scramble the critical phase, to verify that hardy coincidences disappear when the setup no longer fits the logic. If you want a field guide to reading hardy data with integrity, carry 3 habits. Habit 1. Tie every paradoxical claim to the exact calibration steps that justify it. Don't say dark means overlap, unless your single device scans show the intended interference null, and unless you've ruled out sneaky leaks. Habit 2. Keep a ledger of trials, not just successes. Heralded sources and timestamp detectors let you calculate rates per attempt, which exposes selection effects. Habit 3. Test counterfactuals responsibly. Run the alternative middle settings in separate, well-matched batches, and resist the urge to combine statements that belong to mutually exclusive configurations. With those habits, Hardy's setup turns from a party trick into a precision probe of non-local structure. It shows you that the quantum world coordinates device-level facts in a way no local, pre-written root stories can emulate, yet it does so without enabling messages faster than light or letting you win bets by retroactively picking paths. And the soft closing lesson, the one you can carry to other puzzles, is this. Paradoxes shrink when you hold them to operational detail, but they don't vanish, they clarify. Hardy's scheme teaches you to respect how individual inferences, perfectly valid when devices stand alone, can collide when contexts overlap. It invites you to calibrate deeply, to measure gently when you must, and to accept that where things were and what caused what are not universal labels you slap on nature ahead of time, but summaries earned by the specific questions you asked and the quiet competence of the apparatus you built to ask them. Quantum pigeonhole, packing without sharing. Fill 3 travelers into 2 rooms, and in ordinary life, you're guaranteed that at least a pair must share a room. The pigeonhole principle is as sturdy as counting itself, so the claim that quantum mechanics lets 3 pigeons inhabit 2 holes with no 2 ever sharing sounds like a conjurer's boast until you slow the setup and see the hidden hinge, not a repeal of arithmetic, but a reshuffling of what counts as a fact when you prepare and filter carefully so that pairwise same room evidence cancels out even as the head count still adds to 3. Start with the classical rule you trust. If you distribute 3 solid marbles into 2 drawers, opening both hearts of the problem at once, asking for exact locations, you must find a pair together. The principle assumes that each marble carries a definite address at the moment you count. Now build the quantum version with an eye for operational honesty. You prepare 3 particles, so each one has a quiet chance to go left or right inside an interferometer. Call those the 2 holes. But before they reach the end, you don't yank open drawers. Instead, midstream you set devices that can test a yes-no question for each pair. Are these 2 in the same hole or in different ones? Crucially, you design these pair checks to be gentle enough not to blow up the interference that keeps the whole effect alive. And you promise that at the end, you will only keep the runs that pass a chosen final filter, a post-selection that acts like a bouncer at the exit. When you run this carefully, timings aligned, light indistinguishable, leakage suppressed. Something startling appears in the retained data. For each pair considered in isolation, the same hole indicator stubbornly refuses to light up, as if no 2 particles ever shared a room in the trials you kept. And yet the total number of recorded particle arrivals is still 3. Read sloppily, it sounds like a loophole in logic. Read properly, it's a lesson in context. The classical pigeonhole guarantee presumes that the addresses exist jointly and can be read without changing them. The quantum recipe denies that presumption. Those addresses are not fixed stamps but context-dependent records born of interactions. The middle pair check and the final filter form a linked story, and the property, these 2 were in the same place, is not a standalone label that all three pairs can wear consistently across that story. Think of the mid-run pair check as a parity turnstile. It couples to a pair only to the extent needed to register together without leaving the kind of fingerprints that would ruin the end filter. And it does so in many repeated shots, so that tiny nudges add up to a clear picture. In that gentle regime, the aggregate pointer reports for each pair line up with different, while a compensating negative trace, an anti-correlation, hides in the third, unprobed structure, so that the full accounting still respects that you had three objects passing through two routes. Nothing supernatural has happened. You never catch a single run where all three pair indicators flash at once, because you never ask all three strongly at the same time. Instead, you collect separately the statistics for pair AB, for AC, and for BC among the same kind of post-selected exits, and each separate batch says different with near certainty. Try to enforce different simultaneously for all three with a decisive, invasive probe, and you destroy the delicate interference that made the effect appear. This is why the quantum pigeonhole effect does not cancel arithmetic. It cancels a tacit assumption behind the arithmetic, that properties measured in different, incompatible contexts can be stitched into a single picture after the fact. Experimentalists who tested the claim were careful about this. With photons, each hole becomes a well-defined optical path. Each pair check becomes a small interaction at a beam splitter or a controlled phase gate that flips a faint meter only if the pair shares a path. And the post-selection is a specific click pattern at the exit that keeps a sliver of runs. They verified indistinguishability with hallmark tests, stabilized phases, so that same and different really refer to the intended path structure, and ruled out mundane leaks, stray reflections that mimic difference. Some groups used nuclear spins in molecules and tailored radio pulses to embody the same logic. Others explored solid-state qubits, where the parity check is a gentle 2-qubit gate that can be dialed from whisper to shout. Across platforms, the story that survives scrutiny is the same. When you define the middle question and the exit filter as a pair, the kept sub-ensemble refuses to exhibit pairwise sameness, even though the total flow of particles is intact. What do you learn from this besides a party trick? First, you learn to respect that where something was in quantum experiments is not an all-purpose tag, but a claim tethered to how you intend to use the information later. Pairwise, same-box statements drawn from one context can clash with each other when you try to treat them as if they were classical facts that must cohabit. Second, you discover a design principle for quantum technology. You can engineer circuits where destructive two-body coincidences cancel, suppressing certain kinds of collisional noise without damping the overall throughput. In photonics, that intuition helps in routing schemes where you want many carriers to pass without bunching. In sensing, it tells you how to filter a multi-particle signal so that the presence of any particular pair is hidden while a global signature survives. Third, you sharpen your ear for misleading rhetoric. The claim, 3 particles in 2 boxes with no 2 together, isn't a license to violate counting. It is shorthand for given the prepared entrance and the kept exit, the middle time pairwise records that would have shown sameness if we had asked for them do not appear in the data we retain. You can't harvest those pairwise no answers to build a device that transmits impossible information, and you cannot chain them to deduce a contradiction, because each no belongs to a counterfactual test that would, if enacted strongly, remove the very exits you conditioned on. A healthy skepticism asks for failure modes. What if slight distinguishability creeps in so you accidentally mark paths and bias the pair check? What if your detectors miss more events when 2 photons happen to travel together, faking the absence of sharing? Properly done, experiments put guardrails against these. They measure per attempt rates using heralds so that missing events are counted honestly. They scan path delays to show that the effect fades when indistinguishability is spoiled. And they flip the roles of the pairs to demonstrate that the no sharing report tracks the intended logic rather than a static defect in the apparatus. With those controls in place, the effect becomes a tool rather than a slogan. The wider philosophical payoff is gentler than scandal. It's contextuality with a human face. The pigeonhole principle is safe when its premises hold. Definite, context-independent placements exist at once. But quantum experiments invite you to check which premises you have quietly imported. When you ask about AB, you are embedding a little machine that defines same within a full narrative that includes what you will later keep. When you ask about BC instead, you embed a different machine, and nothing obliges nature to honor both embeddings at the same time without changing the outcome statistics. So the soft closing thought you can carry out of the lab and into your own reasoning is this. Paradox whispers when you try to assemble answers from questions that were never posed together. In a world that allows interference, certain pairwise shadows can all vanish while the body casting them remains. Your job as a careful thinker is to declare your questions and your filters up front, accept that not all reasonable tests commute, and learn to design situations where the impossibilities you need are the impossibilities your apparatus truly enforces. Packing without sharing, not by breaking the rules of counting, but by choosing, with surgical timing, which kinds of sharing you ever give your experiment a chance to record. The Quantum Cheshire Cat Storyboard. Imagine sketching a storyboard where a cat walks down a split corridor and, in the next frame, its grin strolls off through the other hallway without the cat. Absurd in cartoons, yet in the lab, a carefully staged sequence of preparations, feather-light probes, and final filters can make a particle's presence trace show up along one path, while a property like its polarization or spin leaves its fingerprint along the other. A quantum Cheshire cat that teaches you how attributes are recorded and how context carves what you're allowed to say. Begin with the cast and the set. A single particle, photon or neutron, is prepared so it can travel through an interferometer with two arms, left and right, while also carrying an internal tag. You choose a pre-selection that quietly spreads the particle across both arms in a balanced superposition and also ties its internal tag to a particular angle. Then you promise that at the end, you will keep only those runs that trigger a very specific detector and tag condition, the post-selection. Between these bookends sit your camera crew, two extremely gentle probes that never slam the door on interference. One probe couples to path. Think of a microscopic pointer that shifts slightly if the particle passes the left arm and the other way if it passes the right. The second probe couples to the internal tag, an equally tiny rotation or phase nudge that registers if the polarization points a chosen way at that point in space. Crucially, each probe is so weak that no single trial tells you much. Only after you gather a large batch of runs and average the tiny pointer shifts do you read a clear signal, and even then, you only keep the subset that satisfies the final filter. Now watch the frames. When you look at the retained data, the path probe shows a robust shift in, say, the left arm, evidence that the particle's presence left a trace there in this post-selected sub-ensemble, while the tag probe shows its signature almost entirely in the right arm, as if the grin chose the opposite corridor. In stronger measurements, you never see a particle split or a grin alone. The effect lives only in this gentle, conditional bookkeeping. That is the first place to clear away confusion. Nothing literal has detached from anything. The cat and the grin are different kinds of records. Path probes interact with where the particle can be said to leave a tiny wake without squashing interference. Tag probes interact with the internal degree of freedom. By arranging the beginning and ending so that the tag flip complements the path structure, you make the average path trace pile up on one side, while the average tag trace piles up on the other. Try to catch both strongly at once, and the trick dies. You collapse the superposition that the story relies on, and the frames revert to dull classicality. This is why the Cheshire Cat is not a loophole in conservation laws or a transporter of free energy. If you put a block in the empty arm where the grin roams, the overall success rate of the post-selection changes in exactly the way that tells you a non-trivial tag interaction was happening there. Remove the block and the rate returns, but you never extract two independent particles worth of work from the two arms, and you never signal faster than light. The signals are tiny, statistical, and tethered to the final filter you chose. In real experiments, the storyboard becomes delightfully concrete, Photonic versions use calcite beam displacers or beam splitters to form two stable paths. A thin glass plate or an electro-optic modulator acts as the path probe by adding a barely measurable tilt or phase. A weak polarization rotator, like a crystal with a whisper-level birefringence, acts as the grin probe. On the neutron side, interferometers carved from perfect silicon split and recombine coherent neutron beams. A small magnetic field in one arm plays the role of the grin coupler by nudging the spin. A faint absorber or phase shifter plays the path probe. In both platforms, stability is everything. If the phase between arms drifts, the careful cancellation that makes presence here, property there, is washed out. If stray light or vibrations leak which path information, the grin smears back into the cat and the effect fades. So teams lock temperatures, servo path lengths with piezo stretchers, check indistinguishability with hallmark interference dips, and track per attempt counts so selection isn't cheating them. Once the plumbing behaves, the data teach you 3 operational lessons. First, context matters twice. The meaning of where the particle was depends on what you will accept as a successful ending, and the meaning of which property it had there depends on how gently you asked. The paradox dissolves once you anchor each sentence to the full script. Preparation, mid-run probe, and post-selection, rather than treat was and had as eternal labels that must hold in a single global ledger. Second, weak probing is not a coy cousin of strong measurement. It answers a different question: which way does the pointer lean on average for the sub-ensemble we kept? And because of that, it can report strange-looking totals, including tiny negative or amplified shifts, without licensing science fiction claims. Those odd averages are not ghosts. They are the footprints left by interference when you condition on a future event. Third, the storyboard is useful, not just cute. In metrology, separating presence from property guides you to place delicate sensors in the arm where they couple to the feature of interest, while routing loss-sensitive components where the particle's occupancy, in the kept runs, is minimal, an architecture that can reduce damage in imaging or boost readout contrast in qubit circuits. In diagnostics, the same logic lets you map how information flows through a complicated interferometer without tearing down the interference you are trying to preserve, a practical way to align integrated photonics or to locate unintended leaks. Philosophically, the Cheshire cat tempts you to overreach. The particle was here while its spin was there. But the sober reading is richer than the slogan. You are learning how statements about systems are really statements about records, and records are things that get written by interactions whose strengths and timing you control. The grin separates only because your end condition selects the histories where the spin-sensitive kicks line up in one arm and the path-sensitive kicks line up in the other. Change the end condition, and the separation pattern redraws itself. That dependence is not a bug. It is the content of complementarity wearing modern clothes. So the gentle closing frame is this: keep drawing storyboards when quantum narratives feel slippery, but label each panel with the question you asked and the promise you made at the end. Do that, and the cat and grin tale stops being a paradox and becomes a design language. One where you learn to place touch where it matters, to let absence carry information, and to accept that in a world with interference, where and what are not indeletable ink on the same ticket, but coordinated captions that only make sense when you view the whole sequence from first sketch to final cut. Interaction-free mind detection refined. Suppose you're asked to find out whether a warehouse contains a hair trigger mine that explodes if a single photon touches it, and you're told you can only use one photon. Ordinary common sense says your test either sets it off or learns nothing. Yet interaction-free measurement rewrites that bargain, and the refined versions show how to push the chance of discovery arbitrarily close to certainty, while making the chance of detonation arbitrarily small. Not by cheating physics, but by arranging the question so delicately that the possibility of an interaction steers the outcome without the interaction actually happening. Begin with the core trick in plain language. You send a single photon into an interferometer where two paths later reunite. If both paths are open and indistinguishable, The photon always exits the bright port and never the dark port because the waves cancel there. Now place a suspicious object, a perfect absorber that would blow if light hits it, into one arm. If the mine is present, the interferometer is no longer balanced, and the photon sometimes emerges at the dark port, a signature that can only occur if the other arm was blocked by something you never touched. That's the Elitzer-Vaidman bomb test in a nutshell, and already it's counterintuitive. A click at the dark port tells you a live device is there, even though the very click certifies the photon took the safe route. But the basic scheme wastes chances and still risks detonations. The refined story is what you came for. Replace the single pass with many gentle glances, and you get the quantum Zeno version. Instead of making an all-or-nothing superposition that fully occupies both arms, you rotate the photon's which path state by tiny angles through a sequence of coupled stages. If the mine is absent, all the little rotations add up coherently, and the photon ends at the bright port with near certainty. If the mine is present, each tiny rotation is watched by the possibility of absorption, which repeatedly nudges the evolution back toward the safe state, locking the photon out of the dangerous path. The upshot is that a final dark port click announces mine present, with an efficiency that grows as you make the steps smaller and more numerous, while the probability of an actual absorption plummets. In the lab, this isn't a fairy tale, but a choreography of optics. You can implement the rotations with birefringent plates or electro-optic modulators, use calcite displacers or beam splitters to separate and recombine paths, and drive the chained interrogation through loops so the photon samples the setup tens or hundreds of times. Heralded single photon sources confirm each attempt, and high-efficiency detectors with low dark counts guard against false alarms. The engineering choices matter because the effect is fragile. Phase must stay locked so that the bright port remains truly bright in the no-mine case. Polarization must be pure so that the tiny rotations add rather than scramble. Any leakage that smears which path information will make the dark port glow for the wrong reasons. When done well, you can exceed 90% interaction-free efficiency in proof-of-principle runs and, in principle, push arbitrarily close to 100% as losses fall and cycle counts rise. Though practical trade-offs, absorption in optics, detector dead time, timing jitter, limit how far you can climb before error modes dominate. The refined protocol also teaches you honesty about evidence. There are 3 outcomes with clean interpretations: bright port, all clear; dark port, mine present; and boom, which you designed to be vanishingly rare. But because real detectors sometimes click when nothing arrived, and real sources occasionally misfire, teams calibrate rates per attempted photon, not per registered click, and they run dummy trials with a known transparent object to measure the background dark port rate. Only when the conditional likelihood of a dark click given mine present dwarfs the baseline do you claim success. Critics sometimes ask whether the photon really avoided the mine, or whether the threat merely influenced a probability. The refined answer is operational. You recover the device intact because the interaction you feared did not occur. No absorbed photon, no deposited energy, yet the alternative possibility of that interaction was part of the physical wiring that drove your outcome. Causation here is not a shove but a veto that shapes what histories remain. If you want intuition, imagine a corridor where a guard might be posted. You don't need to bump the guard to learn he's there. If his mere presence forces every traveler to take the other corridor, the pattern at the far exit already tells you. The refinements make that logic robust against cheating. Consider imperfect minds that sometimes fail to absorb or explode. By tuning the Zeno sequence so the dangerous arm is interrogated in many slivers, you amplify the evidence across tries. A truly live absorber will repeatedly project you back towards safety, while a dud will let coherence survive and send you to the bright port. By comparing rates over many heralded attempts, you classify devices with high confidence without ever paying the full price of a direct hit. Beyond minds and metaphors, interaction-free methods become tools. Damage-free imaging lets you map whether a light-sensitive sample blocks or transmits without delivering most of the light that would have bleached it. In some architectures, you can even concentrate the test into a tiny portion of the sample while reading the outcome elsewhere, protecting fragile regions. Similar logic sharpens counterfactual protocols, where a computer or sensor in a remote arm appears to influence a result even when, in the successful runs, no photon entered its box. The sober reading is not that information traveled without any physical carrier, but that the possibility of an interaction was enough to sculpt the interference. So the final record carries a trace of what would have happened if the path had been taken. Again, a veto shaping histories, not a ghost courier. Real-world twists keep the story grounded. Timing mismatch between the two paths can mark photons and wreck interference. Labs erase it with delay lines and broadband filters. Back reflections concede fake dark port clicks. Designers tilt and isolate optics and perform control scans, where the critical phase is deliberately detuned to prove the mind-present signature vanishes as it should. Detector afterpulsing can mimic a streak of dark clicks. Experimenters vary the repetition rate to watch the artifact recede. Even the definition of interaction-free must be handled with care. You mean no absorption, no energy deposition at the object. But the electromagnetic field did extend into the region. What matters is that the object did not register a hit. Framed this way, you see why the technique doesn't break conservation laws and doesn't let you peek at arbitrary properties without disturbance. It works for yes-no questions, where the mere availability of a destructive channel can be used as a gate to the interference. The practical art is to phrase your question as a gate. Is the absorber there? And then to build an interferometer that translates the answer into where a single photon lands, with failure costs driven as low as components allow. The gentle closing thought is that interaction-free detection isn't magic, it's manners. You learn to ask questions that a fragile world can answer by hint, not by impact. And you train your apparatus to listen for those hints by protecting coherence until the very end. In a culture that often equates knowledge with breaking things open, there's something quietly radical in discovering by not touching. Engineering sequences where the possibility of harm protects you from harm, and the absence of a flash becomes the brightest signal in the room. Maxwell's demon with modern costs. Imagine a tiny doorkeeper perched between two chambers of gas, opening a trapdoor for fast molecules and closing it for slow ones so that, without spending a drop of fuel, heat seems to flow from cold to hot, and a little engine could run forever. Maxwell's demon was meant as a provocation, not a loophole, and the modern lesson is sharper than it can't work. It can work only to the extent that you pay the real costs of learning, storing, and using information, and those bills show up as heat and entropy somewhere in the total system, including inside the demon's head and memory. Start gently with the simple model that crystallized the idea. One particle in a box is measured to learn which half it occupies. Then a piston is inserted on the empty side and allowed to expand, extracting work as the particle pushes. From the outside that looks like free energy from knowledge. One bit of location information lets you harvest a bit of work against the surrounding thermal jostle. The fix isn't to forbid measurement or deny the work. You really can extract energy guided by information, but to notice that after a few cycles, the demon's memory is clogged with records of where the particle was, and to be ready for the next cycle, the demon must either carry an ever-growing hard drive or erase old bits. Erasure is the quiet turnstile where the second law collects its dues. Resetting a memory to a standard blank state squeezes many possible microstates into one, and that compression must dump at least a tiny, quantifiable amount of heat into some environment, a cost bounded by the famous K times T times ln2 per bit. In other words, information is physical, and changing the aboutness of a memory, whether it says left or right, 0 or 1, requires rearranging matter and energy in the hardware that holds it. But the modern story doesn't stop at that clean slogan. It adds a fuller ledger of costs that a real demon must pay to operate at all. Measuring isn't free. You must couple to the particle with a sensor that itself fluctuates and then amplify that whisper of a signal into a robust record that resists noise. Control isn't free. Moving doors, inserting pistons, or updating. Fields takes energy and time, and doing it quickly injects extra dissipation because fast manipulations drive systems away from the gentle, reversible paths that waste the least. Communication isn't free. If the brain of the demon sits apart from the trapdoor, sending the measurement result down a wire and receiving an open or close command burns energy. Even correctness has a price. Errors in measurement or control reduce the useful correlation between the demon's record and the particle's state, and the work you can extract is limited by that correlation. In clean language, the best case extra work you get from knowing something is proportional to how much you actually know, not how much you wish you knew. When researchers built tabletop demons, colloidal beads trapped by laser tweezers, single electrons hopping between tiny islands, magnetic grains in a double well, they watched this balance play out in real time. A camera or charge sensor gathers a stream of noisy data. A feedback controller nudges the system uphill when it is about to slide down. Averaged over many cycles, the controller harvests work from thermal randomness, but the energy burned to capture, digitize, and act on that randomness shows up as heat in the controller's electronics. Nothing in the second law forbids such rectification. It only insists that when you draw the boundary around system plus demon plus memory plus readout, the total entropy budget stays honest. That honesty deepens your intuition about order. B. The gas on one side of the door really does get cooler while the other side heats up. The entropy you removed from the gas flows into the demon's memory and then into whatever heat sink absorbs the erasure, often ending up as a slightly warmer environment or a drained battery elsewhere in the setup. You didn't beat the second law. You moved entropy around using knowledge as your handle. And the handle itself has limits that engineers can feel. If you wait long enough and act gently, you can approach the minimum costs. But then your demon's power output dwindles. Speed costs extra. If you try to coordinate many degrees of freedom at once, the controller's complexity, and thus its internal dissipation, rises. If the world around your demon drifts, the calibration that once harvested work now feeds it back, and your demon becomes a heater. Even in biology, where molecular machines dance at thermal scales, you find the same trade. Enzymes and molecular motors use information about binding shapes and chemical gradients to bias motion and do useful work. But building and resetting those informational states costs ATP and throws heat, and natural selection tunes the balance rather than abolishing it. The reflective punchline is that the demon didn't die. It grew up and took a job description in modern technology. Feedback cooling of tiny mechanical resonators, error-correcting protocols in quantum processors, and adaptive microscopes that dim light only where a sample can tolerate it. All are tamed demons that trade measured information for extracted performance, all are bounded by the same accounting that ties bits to joules. The myths are what we erase. We no longer pretend that intelligence floats free of thermodynamics, or that cleverness can harvest infinite order from noise. We accept that knowing is a physical act, that forgetting is a warm one, and that any machine that claims to outwit the second law has merely hidden its waste off stage. The empowering side of that acceptance is design clarity. When you plan a measurement or a feedback loop, ask what information you truly need, where it will be stored, how often it will be erased, how fast you must act, and which reservoir will pay the bill. Then you can place sensors where they collect the most useful correlation per unit heat. Compress data before you move it. Reuse memories instead of constantly resetting them, and choose cycle times that balance power against dissipation. Seen. This way, Maxwell's demon stops being a gremlin and becomes a graduate course in discipline. Extract what you can from chance, but keep an honest ledger for the information that made it possible, because in the physical world, there are no free answers, only trades between knowledge, energy, and time. And the art is to make those trades in ways that light your devices without quietly burning the room. The quantum demon that pays Landauer. Picture a watchful sprite that doesn't just peek and push gas molecules but runs a quantum lab in miniature. It entangles a memory. Qubit with a single particle engine steers outcomes with feedback pulses and, crucially, keeps a tidy ledger for every bit it learns and every bit it forgets. Because in this story, the demon pays Landauer openly, and you get to see the receipt rather than a hand-waving IOU. Start with a clean scene. A two-level system sits in contact with a warm environment. Left to itself, it jitters, sometimes climbing, sometimes dropping, wasting the tiny free energy gradients that pass through. The quantum demon couples a memory to that system in a way that is gentle and, at first, are logically reversible. A pre-measurement correlates the memory with the system without yet blasting away delicate superpositions. Think of it as laying down a blueprint that says, if the engine is high, my memory tilts this way. If low, it tilts that way. But the tilts are small enough that, in principle, one could unroll them. That distinction matters because the irreversible step, the one that bills you, isn't the initial touch, but the moment you amplify the whisper into a definite record you promise to use. Once the demon reads its memory as an ordinary fact, it can act. When the engine is high, it applies a feedback pulse that channels that energy into a little capacitor or lifts a microscopic weight. When the engine is low, it waits or uses a different move that doesn't waste effort. Run many cycles, and yes, the demon harvests work from thermal motion, the way a miller siphons power from a stream. But now keep your eyes on the ledger. Those memory bits accumulate. If the demon never erased anything, its hard drive would swell without bound. Any finite agent must sooner or later reset. Landauer's insight is crisp even here. Compressing either high or low back into a standard blank state squeezes many underlying micro-configurations into one, and that compression must dump heat somewhere, into a resistor, a phonon bath, a radiative mode, by at least an amount tied to the temperature of that somewhere and the 1 bit's worth of uncertainty you removed. Quantum mechanics doesn't erase this bill. It itemizes it. If the demon's pre-measurement created entanglement that you then ignored by making a classical record, the missing information hides in correlations between engine, memory, and environment. You can delay the payment by storing the messy joint state, even shuffle costs among subsystems by being clever with coherent control. But the moment you clean house, reset memories, discard correlations, return auxiliaries to a ready state, the heat shows up. You can lower the bill by erasing into a colder reservoir, or by compressing multiple messy bits into a smaller number of clean bits with algorithmic tricks. Just as you can cut trash pickup costs by compacting your waste, you cannot erase the bill by rhetoric. Modern quantum versions sharpen the rule rather than soften it. The extra work you pull from feedback is bounded by how much you truly learned, not how much you boast you learned, and how much you learned is a physical quantity you can measure from the quality of your correlations. If your measurement had back action that scrambled the engine more than it informed you, your net gain shrinks. If your detector was lazy or your timing off, your memory holds little of value and your feedback mostly heats. The demon's craft is to engineer the whole cycle so that each joule burned on sensing and erasing buys the most useful correlation possible. In superconducting circuits, that looks like a qubit engine, probed by a nearly non-invasive microwave tone, whose tiny phase shift gets amplified by a cryogenic amplifier into a 1-bit verdict, followed by a fast conditional pulse that pushes energy into a storage mode. The electronics that digitize and store the verdict then warm a resistor every time they clear their buffers for the next shot. In trapped ion or spin systems, that looks like repeated weak glimpses that gradually pin down the state with minimal disturbance, each glimpse recorded in a memory register that must be recycled, with heat dumped into a carefully chosen bath so it doesn't sneak back and spoil the engine's gradient. Even the seductive quantum tricks, erasing against a squeezed, structured, or non-equilibrium reservoir, parking information in long-lived coherences, performing reversible pre-measurements you later undo, only change when and where you pay, not whether you pay. Store the demon's records as entanglement and you can, for a time, dodge a hot erasure. But once you decouple the helpers and return them to their ready states, the correlations you discharge splash entropy into some sink. Switch to a colder sink and you slash the invoice's unit price. Now you're not violating the law, you're running a refrigerator to subsidize your bookkeeping. The most beautiful twist is also the most practical. When you accept Landauer as a design constraint, daemons become devices. You can budget the number of bits you need to measure, compress them before you move them, erase them only when it's cheap, and reshape control pulses so measurement back action does useful pre-cooling instead of waste. You can even price the value of partial knowledge. A fuzzy 2-bit estimate might be more profitable than a perfect 8-bit log once you include the cost to acquire and reset it. And, in quantum error correction, you meet the largest tamed daemon of all, a controller that constantly learns where noise struck and applies fixes. The extracted order buys you coherent computation, but the syndrome records must be reset relentlessly, and the heat they release is why cryostats hum. Step back, and the ethics of the ledger become clear. A daemon that beats the second law is just a description with the boundaries drawn too small. Expand the boundary to include memory, controller, amplifiers, interconnects, and the bath they lean on, and the numbers balance. That doesn't make daemons boring. It makes them honest machines whose performance lives at the intersection of information quality, control finesse, and thermal engineering. The soft closing thought is that Landauer's price tag isn't a scold. It's a compass. It points you toward architectures where knowing just enough, at the right time, with the right memory discipline, lets you skim order from noise without kidding yourself about where the heat went. Build your quantum daemon under that compass, and you'll find no miracles, only a deeper craft. Learn precisely, act sparingly, erase wisely, and let the receipt for every beautiful bit be part of the design, rather than an apology stapled on after the fact. Quantum telepathy? What teleportation isn't? If you've ever pictured quantum teleportation as a sci-fi beam that reads your atoms here and reassembles them there, or as spooky mind-to-mind messaging, park that image at the door. Because what physicists actually do is stranger, subtler, and far more honest. They transfer a state, not a thing, and they can only do it by spending a pre-shared entanglement link and sending ordinary, light-speed messages that tell the receiver how to finish the job, which means no faster than light whispers. No brain reading and no Star Trek disassembly line, yet an astonishing verifiable way to move the shape of information from one system to another without the delicate state ever crossing the space in between. Start with the cast kept simple. Alice has an unknown quantum state, a qubit in a configuration so fragile that trying to copy or peek at it would ruin it. Alice and Bob already share an entangled pair, like a perfectly correlated coin whose outcomes make sense only together. And Alice can phone Bob with 2 ordinary bits after she does something decisive. The heart of the protocol is a joint measurement on Alice's 2 qubits, the unknown one and her half of the entangled pair, that projects them into one of 4 tidy patterns. The catch is that this Bell measurement scrambles and destroys her original in the very act of learning which pattern she got. Those 2 classical bits she sends are not an afterthought, they're the steering wheel. Bob uses them to apply a small, reversible fix to his qubit so that its state now is the state Alice started with, as if the personality of her qubit hopped across the link while the body stayed behind and forgot who it was. That is the first and loudest myth to retire. Teleportation isn't copying a thing, it's relocating a pattern, and because the original is consumed, we never violate the no cloning rule that keeps quantum information from being spammed endlessly. The second myth folds once you follow the wiring. There's no telepathy because entanglement by itself carries no usable message. Unless Alice also sends her 2 ordinary bits, Bob's qubit looks like featureless noise. Those bits cannot outrun light, so no message outruns causality. Entanglement is a shared recipe book you agreed on before the show, not a hotline that lets you think words into someone else's head. The third myth dies in the lab's glare. You don't teleport atoms or people. You teleport carefully prepared states of carriers you can control. Photons across fibers and free space. Ions across traps. Spins across solid state defects. Superconducting microwave states across chips. And the method is picky about noise. Fibers absorb, free space twinkles, detectors miss, and the very operation that identifies a 2-qubit pattern can be hard to do with full coverage. So practical teleportation wears the scars of real hardware. Fidelities that must beat best classical limits to be meaningful, error bars that reflect timing jitters and mode mismatches, and network designs that use clever tricks, entanglement swapping and quantum repeaters, to stretch reach without asking any single link to be perfect. If you want intuition without equations, think of teleportation as moving the alignment that makes a musical instrument play a specific note. The instrument at Bob's end exists and can play. Entanglement gives you a shared tuning fork that correlates your pianos. The bell measurement is you striking a very particular chord that rings through the shared resonance. And the 2 bits are the sheet music note numbers Bob needs to press so his instrument sings exactly what yours would have, had it survived. Because the act of striking the chord at Alice destroys her note, there's no cheating, only the melody persists. And only if Bob gets the note numbers in time. From here, the real story flowers into craft. In optics, teleportation rides on single photons sent through beam splitters and polarizers so that Alice's joint measurement clicks a specific 2-detector pattern, while Bob, keyed by those clicks, rotates his photon's polarization or phase. In ions, a chain of trapped atoms shares entanglement via laser pulses. Alice's joint operation is built from controlled kicks, and Bob's correction is a fast pulse set. In superconducting circuits, the qubits are electromagnetic modes on chips. Entanglement is forged by tunable couplers, and Alice's joint readout is a microwave interference pattern that a cryogenic amplifier resolves. Across platforms, the lesson repeats. The quantum state is too tender to bottle and ship, so you recreate it where you need it. By consuming correlation, you prepared earlier, and by communicating just enough classical information to orient the receiver. Once you grasp that, a half-dozen flashy misreadings fall away. Teleportation doesn't enable mind reading, because thoughts are not single qubits, and your brain's information is tangled up with countless environmental records. Even if it weren't, teleportation demands a pre-shared entangled link, and your cooperation in performing the destructive joint measurement and sending the all-important 2 bits. It doesn't let you bypass distance constraints, because the classical message must traverse the separation at light speed or slower, setting a hard ceiling on how fast the effect can be made useful. It doesn't mass transfer matter, because the recipient already has the matter. What arrives is the instruction set for arranging that matter's quantum configuration, and it doesn't sidestep energy costs or entropy. Generating long-lived entanglement, stabilizing interferometers, cooling detectors and correcting errors all burn resources. A teleportation network looks less like a magic portal and more like a power-hungry, precision-timed orchestra. If anything, the protocol is a humility lesson in how strict the universe is about information. You can't look without disturbing. You can't copy perfectly. You can't steer a distant system's behavior without either sending light-speed help or having pre-installed correlations. But you can do something that no classical scheme can mimic. Move an unknown, unmeasured quantum pattern from here to there with guaranteed fidelity above any guess and prepare strategy, provided you hold up your end of the bargain. That's why teleportation matters. It's the backbone of quantum networking. Entanglement swapping lets 2 nodes that never met share entanglement by having their neighbors perform joint measurements and relay classical outcomes, stitching short links into long ones. Repeaters use memory qubits to store fragile correlations until neighboring stretches succeed, then chain and purify them, so the final link supports high-fidelity teleportation over continental distances. Satellite relays lift entangled photons above most of the atmosphere's mess, so ground stations can share keys for encryption protocols whose security rests on physics rather than promises. In computing, teleportation lets you wire non-neighboring qubits together without physically hauling them across a noisy chip. And, with fault-tolerant codes, it turns into the primitive behind shuttling logical states and injecting special resources a processor can't synthesize on the spot. And in metrology, the same wiring humbles noise. You can teleport away a state before a bad environment mangles it. then recreate it in a safer harbor that finishes the measurement. By now, the closing is gentle because the picture is crisp. Quantum teleportation is a state transfer protocol that spends entanglement and uses ordinary communication to deliver a perfect aboutness from one place to another, while unavoidably erasing the original. Quantum telepathy is a catchy phrase for something the laws of nature have never offered. Message without medium, thought without cooperation, influence without a classical trail. If you want real magic, it's here in the craft. Learning to pre-share the right correlations, to time the joint measurements so they hit the right chords, to protect the classical bits that carry the steering notes, and to accept that what you moved was not matter but meaning. Fragile, precise, and, when the detectors agree and the logs line up, as real as any object you could have tried to ship the old-fashioned way. Time travel qubits and self-consistency. You don't start with wormholes or flashing portals. You start with a question that corners common sense. If a qubit could loop through its own past, what rule would stop it from sending a message that erases the very reason it was sent? And if such a rule exists, what new things could information do under it? From that doorway, the modern conversation about time travel qubits splits into two disciplined paths that tame paradox with self-consistency rather than wishful thinking, and then follow the consequences wherever they lead. The first path, inspired by David Deutsch, treats a closed time-like loop as a system that must enter the past in exactly the state it later emerges with. Not because fate likes circles, but because otherwise your equations spit out contradictions. In practice, this means the looping system finds a fixed point under the interaction you arrange between you in the present and you from the future, so when present you couples to the loop and tries to set up a logical clash, the only states that survive are those that make the whole story self-consistent. That rule has bite. It allows processes that ordinary quantum mechanics forbids, such as perfectly telling apart states that are normally indistinguishable from a single shot, or duplicating a state that you shouldn't be able to clone, because the fixed point condition lets the looping system encode just enough information about the unknown input to break the usual no-go constraints without ever generating a paradox. The second path, often called post-selected time travel, doesn't assume an actual space-time loop. Instead, it mimics the logic of a loop by preparing entanglement, performing a joint measurement that would normally yield many outcomes, and discarding all runs except those that match the one outcome that makes the story consistent, like filming thousands of takes and keeping only the version where the plot has no contradictions. This is a mathematical trick you can approximate in optics and ion traps, and while it doesn't produce real-time travel, it cleanly demonstrates the way conditioning on a future event alters what is possible for the data you keep. Both approaches solve the grandfather-style paradox the same way. They never allow a history in which the contradiction completes. Instead, the dynamics bend to a fixed point, often forcing the loop to carry randomness that diffuses your attempt to force a clash. So the only stories you can actually realize are ones where the message you try to send back fits the world that generated it. Once you accept that discipline, you can talk about power without self-deception. On paper, letting a computer talk to a self-consistent loop rocket boosts what it can solve, because that perfect state discrimination trick turns hard-guessing games into easy ones. Cryptographic schemes that rely on the impossibility of learning a secret from a single noisy sample would crumble in the presence of an honest-to-goodness loop, and decision problems that normally need staggering resources can be cracked by algorithms that query a fixed-point oracle and receive answers that must make the future match the query. But the devil sits in the physical caveats. The mathematics assumes ideal loops and exact consistency conditions, whereas real hardware is noisy, and even the best lab simulations merely emulate the logic with post-selection, where the cost shows up as a tiny success rate and a mountain of discarded trials. There is no evidence that nature gives you closed time-like curves at scales where you can build machines, and every attempt to construct them in classical general relativity leans on exotic spacetimes that likely crumble once quantum fields and gravity's fluctuations weigh in. That skepticism is healthy. It reminds you that time travel qubits are primarily controlled thought experiments and testbeds for reasoning about causality rather than blueprints for machines. Still, the models teach durable lessons. First, self-consistency does not mean determinism in the stifling sense. In the fixed-point picture, the loop often emerges in a mixed state that looks like built-in noise, and that noise is precisely what prevents contradictions. Randomness becomes the padding that keeps logic from tearing. Second, information can appear to come from nowhere in a causal loop. A future device prints a theorem that a past mathematician later proves, and then feeds forward. But in the consistent, descriptions that information is anchored in a global constraint. The loop contains the proof because the solution space only includes stories where it does, not because the universe gifts knowledge free of origin. Third, curious cousins of time loop logic exist in ordinary quantum labs without any claim to time travel. The quantum switch, where the order of two operations is put into a superposition, gives you indefinite causal order and modest advantages in communication, but it does not permit paradox or let you beat no signaling. It's a reminder to label your marvels carefully so you don't smuggle in powers they don't have. Fourth, if real loops were possible, they would shatter the guardrails behind many quantum no-go theorems. So any consistent theory of quantum gravity that truly allows them must also rebuild those guardrails in new form, perhaps by bounding how sharply you can engineer interactions with a loop, or by dressing loops in back reaction noise that neuters the spooky algorithms people fantasize about. In the lab, what you can do today is sober but illuminating. Simulate self-consistency by conditioning on outcomes, and watch how tasks that should be impossible become feasible on the rare runs you keep. Test how tiny imperfections avalanche when you try to chain many such steps, and use these tabletop fables to train your intuition about how causality and information might interlock in any deeper theory. The closing thought is gentle because the terrain is slippery. Time travel qubits are not invitations to rewrite the past or escape responsibility. They are carefully fenced gardens where you learn how to keep logic intact when you let influence trace a loop, and the fence is the self-consistency requirement that blocks contradictions at the cost of injecting exactly as much randomness, conditioning, or constraint as the story requires. Walk that garden slowly, and you come away with better habits. State your consistency conditions before you propose a miracle. Track where the entropy goes when you tidy a paradox. Distinguish genuine causal novelties from clever uses of post-selection. And remember that a universe that forbids contradiction is not dull. It is exquisitely shaped, leaving just enough room for strange circuits of information to exist on paper, while steering real devices back toward the ordinary rule that cause runs forward through light and time. And the only histories that endure are the ones that can bear their own weight when read from start to finish and back again without tearing. Time travel qubits and self-consistency. You don't begin with a gun or a timeline. You begin with a family photo on a kitchen table, the face that had to exist for you to exist, and you ask the unsettling question: if a quantum gadget let you meddle with that past, could you edit the picture and still sit at the table? And if not, what exactly stops the edit? Dressed in quantum clothes, the Grandpa paradox turns from a melodrama about bullets into a lesson about records, constraints, and how consistency quietly rules what stories can be told. First, strip the myth to its bones. I travel back. I prevent my grandparents' meeting, therefore I erase myself, therefore I never travel back. In classical storytelling, this is a logical loop with no exit. Quantum mechanics doesn't fix the loop by granting wish fulfillment. It fixes the loop by insisting that every influence, even a looped one, must thread through a world of physical records that hang together without contradiction. Replace people with stable records, birth certificates, neural memories, photographs, DNA sequences, and you can model the whole question as, can a future interaction rewrite the past while leaving a coherent trail that includes the traveler? In the strictest self-consistent accounts, the answer is calm and brutal. The only histories that occur are the ones that already fit together, which means any intervention you attempt is quietly diffused into an action that leaves the crucial records intact. You don't get the cinematic clash. You get a world that refuses to generate the inconsistent pages of the scrapbook. In practice, that looks like this. Every effort you make to alter the meeting ends up mismatching your intentions. Your message arrives garbled, your timing slips, the crucial door jams, a moment of hesitation alters the outcome, and the reason isn't fate in the mystical sense, but constraint in the physical sense. The full pattern of records that include you must be extendable both backward and forward, and the permissible interactions are those that keep the pattern unbroken. That's not a cheat. It's an admission that macroscopic facts, the meeting, the child's child, are stabilized by a cloud of environmental imprints so thick that any attempt to flip them has to claw through a thicket of mutually supporting traces. Even if you imagine a loop that allows microscopic tampering, those traces act like a safety net that yanks the story back toward the consistent track. But suppose you insist on a sharper scenario. You go back with knowledge that could derail the meeting and you engineer the setting to the brink. Quantum reasoning adds a less dramatic, yet more honest twist. What you can achieve are the outcomes that can be written as part of a single global narrative where the traveler exists, and that often means the world pays you back with randomness instead of catastrophe. The crucial event doesn't swap from happened to didn't under your hand. Instead, countless tiny uncertainties, where a glance falls, whether a car stalls, who spills a drink, shift just enough to blend your interference into a past that still produces you. The randomness is not magic dust. It is the physical slack that keeps logic from tearing. In stories that try to force a contradiction, this slack inflates until your plan dissolves into the one outcome that keeps the ledger balanced. Your letters go unread. Your warning is dismissed as nonsense. The very attempt to sabotage becomes the reason the meeting occurs. If you frame all this in terms of information instead of destiny, the message is crisper. You, the would-be editor, are a bundle of records about a certain past. To undo that past while keeping yourself intact would require erasing those records from every place they reside. Cells, diaries, hard drives, other minds, the environment's microscopic scars, without leaving behind a trace that says they were once there. Physics does not offer such erasers, even at small scale. When you try to rewrite, you export heat, noise, and new records of the rewriting. And those records must fit the very past you are trying to deny. A paradox is not just a conflict of statements. It is a demand that the world hold mutually exclusive archives. Quantum thinking teaches you to count the archives. That is why killing your ancestor is the wrong caricature. The right question is whether you can construct any web of records that contains you, and also contains a clean deletion of the event that made you possible. The answer is no. Either your intervention veers into a harmless cul-de-sac that folds into the history you already had, or the conditions that would have enabled the drastic change simply fail to line up when you try to realize them. You might push further and ask about branching pictures, where many outcomes unfold in parallel stories. The easy mistake is to say, fine, then I jump to a branch where my grandparent never met, and I survive because my original branch still exists. But branching does not give you teleportation rights between finished biographies. It gives you a menu of consistent narratives that never rejoin. In any story where you stand there plotting, the past that shaped you is already entangled with your present. Your very memories and genetic facts are part of the record set that defines that branch. If you use a device that routes you into a story where those facts were different, then by construction, the you who arrives is not the one who remembers planning the sabotage. It is a counterpart grown by a different past with different papers in the drawer. From the inside, no one experiences the contradiction. From the outside, there is no single ledger that lists both you arrived and your origin was denied. Far from being a loophole, this is a guardrail. It keeps talk of changing the past from sliding into wordplay. The interesting physics sits elsewhere, on the edge between fragile microfacts and robust macrofacts, and on the practical question of how far any influence can spread without tripping over the web of existing records. At small scales, you can coherently steer alternatives and later post-select the stories you keep, which mimics some of the logic of tampering with earlier moments. At human scales, you are embedded in an ocean of decohered imprints that make large-scale rewrites functionally impossible. Seen that way, the quantum clothing doesn't glamorize the paradox. It domesticates it. It says that causation is not a simple arrow you can flick with a finger. It is a tapestry whose threads must all hold, and any move you make must be woven through the whole. This view carries a gentler, practical moral. When you fantasize about erasing a mistake in your family line, you are really asking to subtract records while keeping the consequences that define you. The physics answer is that the world does not maintain debt-free edits. What you can do is different and, in its way, deeper. You can add new records that change how the existing ones are read. You can send a message back in ordinary time that alters the future available to someone else. You can change which stories become robust going forward. In other words, you can steer the only kind of time travel that nature endorses: forward-leaning, record-aware, self-consistent. And the soft closing thought, the one that quiets the melodrama without dulling the wonder, is that consistency is not a prison. It is the reason you can trust the world enough to plan, to promise, to inherit. Quantum mechanics doesn't grant you a license to break your own source. It grants you a language for why sources hold, and a craft for influencing what comes next, without pretending you can unwind what was already braided into the fabric that made you possible. The quantum switch as a detective game. You don't start with time machines or faster-than-light tricks. You start with a whodunit, two suspects. A and B each leaves a faint mark on a delicate clue, and your job is to figure out which suspect did what without smudging the evidence. So you arrange a detective game where sometimes A examines the clue before B, and sometimes B goes first. And then you ask a more daring question. What if the order isn't fixed until the very end? As if the case file itself held both timelines open, and your final readout decides which narrative coheres. That is the quantum switch in plain clothes, a device that puts the order A then B and B then A into a controlled superposition, so that the relative order becomes part of the quantum state you can interrogate. And once you see it that way, the story shifts from paradox to craft. Begin with the stage. A target system carries the clue, a photon's polarization, a spin, a microwave mode, while a control system carries the question, which order? When the control is in one basis state, the lab routes the target through A followed by B. When it is in the other, it routes through B followed by A. And when you prepare the control softly, in a quantum blend of both, the lab literally builds both circuits at once and ties them together so their outcomes can interfere. The hook is not that the operations happen chaotically, it's that the global process has no single before and after that fits every frame. Yet the device remains local and lawful. Each lab, A and B, still sees only a proper input before it acts, records a proper output after it acts, and never receives a message from the future. What falls away is the demand that there exist a ground calendar entry saying A precedes B or B precedes A for the entire run. Instead, the control system is the case log that keeps both possibilities live until you read it. Why care? Because certain mysteries are unsolvable if you lock the order in advance. Suppose A and B are noisy filters you don't fully trust. Individually, they blur the clue. And if you commit to a fixed order, you can't tell whether the pair hides a subtle non-commutativity that matters for your application. With a switch, the interference between the two orders amplifies exactly that non-commutativity into a measurable signature on the control, letting you diagnose A and B don't play nicely together without ever needing to force clean access to either box, or consider communication with constraints. Two parties each apply a transformation to a message, but are forbidden from knowing who acts first. Classically, that ignorance wastes capacity. Yet the switch architecture lets the receiver recover more structure from the same scrappy resources because the who went first information is not lost. It is encoded coherently and can be read out. Or think metrology. When A and B each inject a dollop of noise that would drown a tiny phase if you probed them sequentially, the superposed order lets the tiny phase beat against itself in two time orders at once and shows up on the control as a cleaner signal. You kept the clue legible by letting timeline and state share the burden of carrying it. If your instincts bristle, Doesn't a superposition of orders violate causality? The detective metaphor helps steady them. No witness is interviewed before they exist. No statement is retroactively edited. Rather, the file structure of the investigation is itself quantum. So the correlation pattern among notes can't be embedded into a single linear narrative that all observers would agree on ahead of time. Practically, labs build switches with unromantic hardware. A photon's path plays the control. Beam splitters fork it into two interferometer arms, and cleverly placed modules apply operation A in one arm and B in the other, so that recombining the paths entangles or disentangles the order with the control. Flip to other platforms and the plot remains. Trapped ions route logic gates conditionally. Superconducting circuits weave microwave pulses through tunable couplers in alternate sequences controlled by a qubit, and acoustic or spin systems do the same with delays and swaps. The engineering headache is stability. To make A then B talk to B then A, the two routes must stay phase-aligned to a whisper, and any stray leak of which order information, tiny reflections, polarization drifts, timing jitter, kills the very interference that carries the advantage. So experimenters temperature lock paths, actively feedback phase, and benchmark with causal witnesses. Specialized tests that certify the process cannot be decomposed into a probabilistic mixture of fixed orders. Once the plumbing behaves, new investigative moves open. In channel discrimination, a switch turns a problem that classically needs many queries into one solvable with fewer, because the control qubit's readout is sensitive to the algebraic mismatch between suspects, rather than just their blunt action on the target. In communication complexity, parties can implement tasks with fewer exchange symbols by encoding the order itself as a resource. In thermodynamic and control settings, you can place disturbing steps in different time slots without committing to which disturbance came first, and extract work or stabilize a system more gently because the two sequences cancel some of each other's damage on the control's ledger. Equally important are the limits. A switch does not let you signal backward in time, does not magically compute uncomputable functions, and does not unlock free energy. When the boxes commute, when A and B behave the same regardless of order, the switch buys you nothing, and when the environment leaks the order, the advantage fades. The conceptual payoff is subtler than speed-ups. You learn that cause can be indefinite without becoming incoherent, that processes can be stitched from locally sensible interactions, yet resist a single global ordering, and that such indefiniteness is itself a usable, characterizable resource, akin to entanglement and coherence with its own witnesses, noise models, and error budgets. This perspective nudges design habits in a practical direction. Instead of asking, which pipeline should I build, AB or BA? You begin by asking whether the task gains from keeping that choice coherent to the end. You place diagnostics on the control to read out the signature that matters, rather than demanding perfect visibility on each component, and you plan for noise by protecting the order qubit with the same seriousness you protect data. The closing move in our detective story is gentle but precise. The quantum switch is not a loophole in logic. It's a new kind of notebook, one that lets you write two sequences in pencil and only ink the timeline when you've squeezed the most evidence from their interference. Handled with care, it teaches you that some questions are not best answered by choosing an order early, but by keeping your options coherent long enough for the world to tell you, through a clean fringe on a single qubit, exactly which aspect of the case was worth knowing in the first place. Locked door evidence, device independence. Imagine hiring two mysterious boxes from a vendor you don't entirely trust, placing them behind locked doors at opposite ends of your lab, and promising yourself you will never peek inside. No schematics, no calibration passwords, no backstage favors, and then asking for something audacious anyway. Show me. By nothing but the patterns of lights they flash when I press random buttons, that there is genuine quantum entanglement between them, that no classical script could fake what I'm about to see, and that the bits I harvest are fresh enough to secure keys or certify randomness, even if the vendor built the boxes to cheat. This is the spirit of device independence. Evidence that holds even when the devices themselves are treated as black boxes, And once you grasp the rules, you understand why this locked door approach has become the gold standard when trust is scarce and stakes are high. The game unfolds in 3 moves. First, you sever easy conspiracies. Generate choices in real time so neither box can guess which question it will be asked next. Keep the boxes space-like separated so that whatever happens in one can't inform the other by an ordinary signal. And keep a ledger that counts every trial, not just the convenient ones. Second, you pose a set of simple, fixed questions. Press one of a few buttons on each box and record the pair of answers again and again, building a table of joint frequencies. Third, you test those frequencies against a threshold that no strategy based on shared classical information can cross. If your data passes the threshold by a clean margin, you conclude not only that something non-classical happened behind the doors, but, more powerfully, you can quantify how much private randomness was produced and how much secret key could be distilled, without ever trusting the vendor's claims about the insides. What makes this remarkable is not the statistics alone. It's the shift in what is being certified. In a conventional lab, you certify components. This detector has a given efficiency. That laser has a given spectrum. The fibers have so much loss. The timing jitter is so many nanoseconds. In a device-independent lab, you certify behavior under constraints. No superluminal communication, measurement choices that the devices cannot foresee, isolation so the boxes cannot leak outcomes to an eavesdropper. Within those constraints, if the output pattern violates the classical ceiling by enough, you get guarantees that are provably independent of the detailed inner workings. From there, the framework blossoms into tools. For security, device-independent key distribution turns clicks into keys with proofs that do not collapse if the detectors were miscalibrated or the source had unintended side channels. An adversary who manufactured the boxes can still be locked out, because any extra knowledge they hope to embed would drag the statistics back under the classical bound, shrinking the certified key until it vanishes. For randomness, device-independent expansion takes a small, imperfect seed of unpredictability, the sort you can squeeze from a mundane randomness source, and, by driving the boxes through many rounds, produces a longer string of bits that are provably fresh even to an all-seeing adversary, with the amount certified directly from the observed violation and tightened by finite data analyses rather than wishful asymptotics. For benchmarking, self-testing emerges from nothing but the correlations you can infer, up to harmless relabelings, which entangled state the boxes must have shared and which measurements they effectively performed. You don't just say non-classical, you say close to this specific state and these specific observables, with error bars born from the same locked door data. The price of such strong claims is discipline. You must mind assumptions so quiet they're easy to overlook. Your choice buttons can't be predictable on the timescales that matter to the devices. Your separation must genuinely block crosstalk. Your detectors must be efficient enough that missed events don't open a back door for classical mimicry. Your analysis must handle memory, because an adversarial box can correlate its answers across many rounds to exploit naive tests. And your proofs must be finite size, turning string lengths and observed fluctuations into conservative guarantees, rather than extrapolations to infinity. Modern protocols meet these demands with craft. They use fast, local randomness to choose settings, hardware layout and shielding to enforce independence, timing windows that close classical loopholes, and extractors that distill near-perfect bits from the noisy harvest, with rigorous accounting for every loss and bias. Just as important as what device independence delivers is what it refuses to promise. It does not claim that your entire facility is secure if sensitive information leaks through cables you forgot to isolate. It does not rescue sloppy engineering that lets side channels broadcast your setting choices in advance. And it does not grant miracles. If the separation collapses or your buttons become predictable, the guarantees collapse with them. Instead, it changes how you argue. Rather than, we measured the detector's efficiency to be X, you say, even if the detector were maliciously chosen, the pattern of answers still forces the amount of private randomness to be at least Y. In this light, locked door evidence becomes a design philosophy. You separate the world into constraints you enforce and behavior you observe, and you write proofs that bind those together so tightly that the vendor's secrets no longer matter. That philosophy travels well. In quantum networks, it guides how to verify entanglement between nodes you don't fully control. In cloud quantum computing, it shapes tests that certify non-classical performance from behind an API. In metrology, it hints at ways to guarantee sensitivity claims without trusting the precise tuning of every component, by tying promises to inequality violations rather than to calibrations. And in foundational studies, it recasts old debates into operational statements. What you can say about nature when all you hold are buttons, lamps, and a stopwatch, not theories about hidden gears. There are pragmatic twists worth knowing. Because real devices are imperfect, you often blend device-independent methods with semi-independent ones that assume, for instance, a bound on dimension or a trust level for a source while keeping the detectors in the dark. These hybrids relax hardware demands while retaining much of the vendor-proof flavor. Because long runs amplify tiny vulnerabilities, you design for composability. The bits you certify must remain secure when combined with other protocols. So proofs track not just averages, but the worst-case leakage under chaining. And because an adversary can stage memory attacks, you randomize test and generation rounds, keep some runs hidden until the end, and audit using entropy accumulation theorems that let you sum small, per-round guarantees into a global bound without assuming independence. What starts as a minimalist setup, 2 locked boxes and a record of flashes, thus matures into a rigorous practice. You pick the inequality that matches your channel and noise model. You choose settings with fresh randomness. You enforce separation in space and time. You log every event, and you translate the observed violation into concrete, finite key or finite randomness claims with error bars you can defend. And the gentle closing lesson, the one that steadies you when trust is thin, is that device independence isn't cynicism dressed as physics. It's respect for evidence. It teaches you to ask only for what the world can certify under constraints you actually uphold, to trade calibration bravado for statistical honesty, and to build systems whose security and truth survive behind closed doors. In a landscape where black boxes are everywhere, from chips you didn't etch to clouds you don't administer, learning to demand locked door evidence is not just good quantum taste. It's a habit of mind that keeps your future instruments honest, your secrets yours, and your claims aligned with patterns that even a skeptical stranger, handed only your button logs and lamp timestamps, would be forced to accept. Non-local games. Pretend you're a referee with 2 locked rooms, 2 buzzers, and a stack of question cards. No cables between the rooms, no whispered plans after. The game starts, and your only job is to see whether the answers that flash back could have been produced by ordinary prearranged scripts or whether the players are quietly using a stranger resource. This is the world of non-local games, where you test ideas about space, influence, and information by turning physics into rules that fit on an index card, and the path from the simplest game, CHSH, to the richer magic square teaches you how entanglement changes what cooperation looks like when communication is banned. In a CHSH round, you send a random bit to Alice in room A and a random bit to Bob in room B. Each must press a button that lights up either 0 or 1, and you tally a win if their 2 bits match or differ according to a fixed pattern tied to your questions. If they only share a plan made before the doors shut, the best they can do averages out to 3 wins in 4 over many rounds, a ceiling set by plain reasoning about all possible scripts that might be written on a note card. Yet when the 2 rooms share a pair of entangled particles prepared long before the quiz begins, and each player's button press corresponds to a gentle measurement on their particle chosen according to the question they receive, the score climbs beyond that classical ceiling to a higher plateau that no clever prearrangement can reach. Still not perfection, but high enough and stable enough that over long play, the pattern of wins can't be faked by any local plan. The significance isn't the number itself, it's what the number certifies. That the world admits correlations which cannot be built from separate pre-existing answers, and that those correlations show up reliably even when you never open the doors to see what machinery the players used. CHSH is the starter puzzle because its rules are spare and its verdict is clear. But it also hides a discipline you'll need later. The questions must be chosen at the last moment so the rooms can't guess them. The rooms must be far enough apart that a signal between them would arrive too late to help. And you must count every round, not just the pretty ones, or you risk fooling yourself about what resource was actually used. Once you make that discipline a habit, you can level up to the Magic Square, a game that looks like a math puzzle from a child's workbook, yet becomes a perfect stage for quantum cooperation. Here, the referee secretly picks a row number for Alice and a column number for Bob in a 3x3 grid. Each player must fill their line with bits that obey a simple parity rule. Rows must add to an even number, columns to an odd number, and at the intersection cell, the two answers must match. With only pre-arranged scripts, there is no way to satisfy all 9 intersection constraints at once. Any table you hand-wave into existence will violate at least one of the parity promises, and the best classical team can do is win 8 rounds out of 9 in the long run. But if the rooms share a carefully prepared entangled state, and choose their local questions as measurements whose outcomes are interlocked by that state, the players can coordinate their row and column outputs so that every intersection cell always agrees and every parity rule is met, even though the rooms never exchanged a word once the door shut. This is not magic. It's consistency enforced by the structure of the shared quantum state. The local questions are tuned so that the product of certain answers on one side must match a product of answers on the other side, and those relations are built into the way the state responds to compatible sets of measurements. The upshot is a cooperative strategy that wins every round while obeying the no communication rule, a demonstration that quantum resources enable flawless coordination. Where classical resources hit a brick wall, what you learn by walking from CHSH to Magic Square is more than a string of high scores. You learn a methodology for turning grand statements into operational tests. Instead of arguing about spooky action, you write a rule set, you run the tournament, you log the lamp flashes, and you compare the win rate to ceilings that any classical model must obey. You also learn that different games reveal different features. CHSH exposes the raw non-classicality of correlations with a clean, universal benchmark. Magic Square shows how the structure of measurements matters, because it transforms what would be a chronic shortfall into perfect coordination. Along the way, you get practical insights that matter beyond the game room. If you want to certify that 2 distant labs share entanglement without trusting their inner workings, you can use a CHSH-style game as an audit tool and tie the observed score to a guaranteed amount of private randomness or secret key, because any device that wins above the classical threshold must be producing outcomes that even a dishonest builder couldn't fully predict. If you want to check that a quantum processor really implements the intended observables, a Magic Square test can self-test the setup. From the pattern of successes you can infer, up to harmless relabeling, the shape of the state, and the directions of the measurements the device effectively used. And if you're building communication protocols, the games hint at a surprising craft. Sometimes the most efficient use of limited channels comes from recasting a task as a game where quantum correlations stand in for messages you're not allowed to send. Equally important are the limits these games make you respect. The players cannot use their correlation to send messages faster than light. The winning patterns are statistical and appear only across many rounds, not as a single miraculous event. And game advantages are not free passes around noise and loss. Real devices miss detections, drift and produce stray clicks, so clean violations require high efficiency, fast and trustworthy question choices, and spacing that blocks backdoor signals. Still, the core lesson endures. By designing questions whose answers are chained together in ways classical scripts cannot satisfy, you turn abstract talk about non-locality into a scoreboard a skeptical outsider can read. Perhaps the most quietly powerful habit you acquire from these games is a new sense of evidence. You stop asking what a black box claims to contain and start asking what behaviors it can sustain under scrutiny. You stop debating metaphors and start comparing win rates to provable ceilings. You treat coordination as a measurable resource, one that can be spent to certify entanglement, to grow fresh randomness, to benchmark devices, or simply to show a student that there is more in the world than common sense separability. And the gentle closing thought: the one that lingers after the room lights are off and the buzzers are quiet, is that the beauty here is not in defiance for its own sake, but in disciplined surprise. Simple rules, clean separations, and honest tallies reveal that cooperation without communication can be stronger than any plan written on paper, as long as the plan was written not by the players, but by the shared structure of a world where correlations can be real, decisive, and yet never carry a whisper of a message across the locked doors you carefully keep shut. Context games, Kochen Specker coloring. Spread a paper map of a strange city and try a child's game. You are told to color each street either red or blue, with a simple rule that any set of streets meeting at a quiet square must follow a pattern. Say, exactly one red among blues, or numbers of reds must add up to a neat total. And you're promised that if the city were ordinary, you could finish the coloring without lifting your pencil. Now let the map stand for a quantum system of 3 or more levels. Let each street be a yes-no question about a property. Let each square be a context where those questions can be asked together without conflict. And you have the Kochen Specker challenge. Can you assign answers to all possible questions in a way that ignores which other questions you happen to ask alongside them? The theorem says no. There is no global coloring that satisfies all the local rules at once. No way to pre-ink the city with context-free truth values that a later measurement merely reveals. You don't need algebra to feel the pressure. You trace one neighborhood at a time. Groups of compatible questions where quantum theory guarantees certain joint constraints. And each local requirement seems harmless, even obvious. But as you wander, edges you colored earlier collide with edges you must color now, and a contradiction blooms. One intersection demands that a particular street be red. A different intersection elsewhere demands that very same street be blue. That is the lesson distilled. In a world with 3 or more dimensional quantum systems, outcomes are not labels attached to questions in isolation. They are records licensed by the entire set of questions you choose to ask together. This is not the earlier story about distant rooms and forbidden messages. Nothing here travels through space, and no one breaks the speed limit. Instead, the oddity lives inside a single system. The incompatibility of a universal pre-written script with the modest demand that measurements in different contexts respect the functional relations quantum mechanics enforces among them. If you picture each question as an arrow in space and each context as a set of mutually perpendicular arrows that can be known together, a Kochen Specker proof is a carefully assembled sculpture of arrows that defeats any attempt to paint exactly one arrow in each perpendicular trio red while keeping the rest blue. Try to satisfy all the trios and you eventually paint yourself into a corner. The educational payoff comes in 3 tiers. First, conceptual. Non-contextual hidden variable models. The ones that say every question has a definite answer, independent of what else is measured. Cannot mimic quantum predictions for such sculptures. The obstruction isn't rare or technical. It is baked into geometry. Second, operational. You can translate the coloring impossibility into tests that real laboratories perform by checking inequalities whose bounds are sacred to any non-contextual assignment, but are violated by quantum data. Here the experiments use quatrits rather than qubits, photons where you track 3 path modes or polarizations, trapped ions with 3 internal levels, neutrons with spin and path combined, to stage sets of compatible measurements and tally frequencies across many runs. If the statistics breach the non-contextual ceiling, you have witnessed contextuality, an empirical statement that outcomes cannot be ascribed in a way that forgets context. Third, practical. Contextuality is not just a curiosity, it powers advantages. In certain models of computation, the magic resources that lift a machine from easily classically simulable to provably hard to simulate are contextual states. measure and feed-forward schemes can be rephrased as games whose perfect play requires colorings no classical ledger can provide. Even in sensing and certification, contextuality shows up as a yardstick. In graph-theoretic language, the structure of compatible question sets bounds classical performance, while quantum strategies push against a different, larger bound. And your data's position between these bounds tells you how much uniquely quantum fuel you are burning. To keep the story honest, you also learn the craft. Contexts must be built so that within each, the questions truly can be answered together. Optical modes aligned, crosstalk suppressed, calibration curves stable. Otherwise, the local rule you think you are testing is not the rule your apparatus actually realizes. You must guard against signaling between sequential steps that could sneak context information into a device that ought to treat each compatible block cleanly. And you must analyze finite data with care, because the contradictions emerge only as stable trends across many trials, not as a single dramatic snapshot. Done well, experiments form elegant minimal sets. 31 directions in three-dimensional space, or 18 observables arranged so each participates in multiple contexts, or ultra-lean 13-ray constructions, whose very minimality makes them robust against drift. The metaphor shifts as you absorb the habit. Stop thinking of properties as stickers that objects wear, and start thinking of your experimental question as a frame that makes certain summaries meaningful at once. Change the frame, and you change which summaries are jointly meaningful. That doesn't make reality slippery in the cynical sense. It makes it disciplined. When you ask compatible questions together, the answers slot into patterns constrained by the theory's geometry. When you mix questions from different contexts, the theory refuses to let you pretend that a single pre-existing label covers both at once. Carry that discipline into design and you discover surprising uses. You can build context games, clever sequences of compatible blocks, for calibrating devices in ways that expose context leakage. If a black box pretends to output context-free, truth values, it will betray itself by failing a coloring inequality that honest quantum gear easily passes. You can plan computations by harvesting exactly those states and measurements whose contextuality witnesses rise above noise thresholds, ensuring that the non-classicality you need is really present rather than hand-waved, and you can teach cleaner intuition. When a beginner asks, "But surely the system has an answer to each question all along," the coloring map is a soft, slow antidote. You let them try to color, neighborhood by neighborhood, until the contradiction stares back, and then you invite the reframing. Outcomes are not hidden in the object like beads in a pouch. They arise as stable records of an interaction whose legitimacy depends on a context that you, as the experimenter, chose. The gentle closing thought is to treat Kochen Specker not as a paradox that steals comfort, but as a guide that gives precision. It asks you to say which questions are jointly askable, to accept that some perfectly reasonable question sets cannot be welded into a single global story, and to build your explanations around records that are true for those sets. When you do, the city you color stops being a trap and becomes a map, one where the routes you pick determine the landmarks that can be named, where consistency lives in neighborhoods rather than across the whole globe, and where learning to navigate by contexts turns a tangle of streets into a calm, comprehensible walk. The Free-Will Loophole with stars. You've probably felt the nagging worry that experiments about spooky quantum links might be rigged by the tiniest bias in how we choose what to measure. So let's face that worry head-on and see how physicists hand the choice to the stars. In a Bell test, you send two entangled particles to distant stations, and at the last moment you pick which question to ask each one. If the world were secretly classical in a particular way, the best prearranged scripts could only win a certain fraction of the time. Yet quantum predictions say you should win more often, provided your choices are genuinely independent of whatever hidden instructions the particles might carry. That independence is the free will, or setting independence loophole. If, somehow, The measurement settings were subtly correlated with the particle's hidden variables. A clever classical model could fake the quantum pattern. Closing ordinary loopholes is engineering. Make the detectors efficient so you don't cherry-pick results. Place the stations far apart so light can't sneak a message across in time. But closing the independence loophole is about causation. You want your setting bits to be born outside the shared past that could have influenced both the particles and your randomizers. Enter the sky. Starlight on its way to Earth carries properties, like which of two colors a photon happens to fall into, that were fixed when that photon left its star. If you use those arriving colors to flip your measurement switches in real time, then any conspiracy that correlates settings with hidden variables must have been arranged no later than the emission of that starlight, sometimes hundreds or billions of years ago. The protocol is conceptually simple, even if the hardware is fussy. Aim small telescopes at widely separated celestial sources. Route each detected stellar photon through a fast dichroic or time-binning circuit that outputs a setting bit. Feed that bit straight into the analyzer that interrogates the entangled particle, and make sure the timing is tight enough that the cosmic photon is registered and converted after the entangled pair is created, but before either particle reaches its analyzer, with the two laboratories spaced so far apart that neither laboratory can receive a light-speed signal about the other's choice in time to help. When everything is space-like separated in this way, the only way for a classical script to coordinate answers with your cosmic choices is for the script to have been choreographed deep in the devices, shared past light cone, pushed back from microseconds to millennia, or to cosmic epochs where the light first started its trip. That step doesn't claim to prove freedom in any metaphysical sense. It makes the remaining conspiracy so large, so ancient, and so intertwined with the fabric of the universe that it stops being a scientific alternative and becomes a philosophical escape hatch. Because ordinary random number generators could, in principle, be nudged by local influences. The star method works like a cleaver, severing common causes. By tying your setting bits to photons born far away, you refuse the particles in the lab a chance to collude through any recent shared cause, and the observed violation of the classical ceiling becomes locked behind temporal doors your devices cannot reopen. Under the hood, the experiment is a triumph of careful bookkeeping. You need entanglement that is event-ready, meaning you herald the creation of each usable pair so you can condition your analysis on well-defined trials. You must characterize detector efficiencies and timing windows, so missing clicks can't sneak in a bias, and you must quantify the tiny rate of wrongly routed stellar photons, misclassifications that could dilute the independence you're trying to guarantee. You also have to worry about mundane astronomy. Stars twinkle, spectra drift, and the atmosphere scatters, so you calibrate your dichroics and time bins against those wobbles and place the telescopes, so each station's sky is genuinely different. That way, even a local saboteur with a floodlight can't imprint a hidden correlation across both labs at once. Some groups push beyond stars to quasars, lighthouses from the young universe, so that any hypothetical coordination would have to be coded before our solar system existed. Others experiment with human choices or radio noise just to stress, test assumptions, but the sky keeps the cleanest causal bookkeeping. If you visualize the space-time diagram, the point becomes serene. Each entangled particle flies into its own future light cone. Each setting bit drops in from a region of space-time that barely overlaps, if at all, with the source's shared past, and the analysis looks only at trials where these regions are clean. Under those constraints, the data's verdict means what it says. The outcomes are more strongly correlated than any local, pre-written plan can achieve, and those correlations persist no matter how you twist dials. Because they aren't born from tailored scripts, they arise from a resource that classical scripts cannot emulate. What remains open after you've done your best with stars is a razor-thin possibility called superdeterminism. The idea that everything, including your decision of where to point the telescopes and which photons happen to be registered, is part of a grand, prefixed tapestry that conspires to produce just those settings that make quantum theory look right. That view isn't logically impossible, but it declines to offer testable wiggle room because it explains every outcome by saying it had to be so. It can't be ruled out by any new separation or older starlight, and it can be made to fit any data whatsoever. In science, we generally set aside such unfalsifiable frameworks, not because they offend our feelings, but because they cannot guide design. They tell you nothing about which knob to turn next. Device-independent methods, where you certify entanglement, secrecy, or randomness from patterns alone, gain their bite precisely because you worked so hard to quarantine your choices. Your keys are private, not because you hoped the generator was clean, but because a classical adversary who knew your devices, guts, could not have produced the pattern of violations you saw without faster-than-light help, or an implausibly ancient conspiracy. This isn't just foundational theatre. It leads to practical habits you can carry into any high-stakes measurement. You learn to separate assumptions you enforce, space-like separation, fast settings, honest counting, from claims you infer, non-classical correlations, fresh randomness, and you design experiments whose conclusions degrade gracefully if the assumptions are slightly nicked, quantifying how much settings bias would be needed to explain away the violation, and checking that your hardware stays far below that threshold. You also learn, perhaps quietly, a more personal discipline about evidence, that independence is not a vibe but a geometry, a statement about light cones and timing margins, that random enough is not a shrug but a quantified bound, and that when you cannot open a black box, you can still let the sky write your questions in a way no local trickster can anticipate. The soft closing thought is that handing your choices to distant stars is less a romantic gesture than an act of respect for causality, for skepticism, for the idea that extraordinary claims deserve defenses built from the oldest light you can borrow. You won't settle every philosophical debate by doing this, and you don't need to. You will have built an experiment whose verdict does not depend on trust, whose logic is pinned to the structure of space-time itself, and whose quiet message to your future self is simple. When independence matters, let the universe make the coin flip, and then listen carefully to what the coins, and only the coins, let you honestly say. Randomness. Oracle versus clever cheater. Imagine you're handed a black box that claims to be a randomness oracle, and across the table sits a patient adversary with time, tools, and a taste for loopholes, the clever cheater. And your task is not to admire pretty coin flip statistics, but to decide, with evidence that survives skepticism, whether the bits that spill out are fresh to the world or merely rehearsed. The quickest way to feel the stakes is to notice how often people confuse unpredictability with irregularity, because sequences that pass cute pattern tests can be generated by short recipes, while truly useful randomness is defined against everything the cheater might know or influence, including factory calibrations, side channels, and yesterday's logs. Start by drawing a mental fence around what the adversary can see and touch. Perhaps they built the device. Perhaps they control the power line or the temperature. Perhaps they aim light at your photodiode or shout radio at your chip. And almost certainly they read your public software. Within that fence, you don't ask, do the bits look jagged? You ask, how well could a cheater who knows the fence predict my next bit before it appears? That shift turns show and tell into a betting game with rules you can enforce. In the weakest setup, you rely on design claims, thermal noise in a resistor, avalanche jitter in a diode, timing edges in oscillators. Those sources are real, but a cheater can steer their averages, drift their gains, or learn the quirks of your digitizer. Standard statistical batteries are necessary but shallow. They flag obvious bias and serial correlation, but cannot certify secrecy because they never model the adversary. So you climb to stronger ground and make unpredictability operational. Instead of trusting a mechanism, you stage a repeated game that no classical foreknowledge can win above a known threshold, and you harvest bits only to the extent the device wins that game. One family of such games lives in non-local tests. You split your hardware into distant wings that answer questions chosen at the last instant, and you verify that the pattern of joint answers beats any strategy built from prearranged scripts. From the size of that beat, you compute a conservative lower bound on the min entropy per round, the adversary's best guess. Success rate is squeezed below a calculable ceiling, and you then compress the noisy harvest with an extractor that turns many shaky bits into fewer, nearly uniform bits, even if the cheater knows most of the raw stream. The extractor matters because raw quantum data can be ugly. Detectors blink, sources wobble, and bias wanders with temperature. A good extractor is a public algorithm with a small secret seed that scrubs structure you expect the cheater to know. Much like a distillery that burns off flavors while keeping the proof. Think of it as insurance that even if the cheater knew 90% of your raw outcomes, the distilled key still hides close to perfectly. But a cunning adversary won't just accept your rules. They'll attack the periphery. They can exploit memory. If your box remembers past settings, it can serve you outcomes that look non-classical in short blocks, while staying globally predictable. They can exploit selection. If your detectors miss many events, a cheater can choose which trials survive and nudge the tallies into a fake win. They can exploit timing. If your setting choices are generated early, a cheater can peek through stray emissions and lean their answers accordingly. The countermeasures are discipline, not bravado. You choose settings from a source outside the device's control, and on a timescale too tight for a causal signal to help. You account for every trial with event-ready heralds, so missing clicks don't become a backdoor. You randomize which rounds are used to check honesty and which rounds harvest bits, so a cheater cannot game the scoreboard. You use finite data mathematics that turns the observed scoreline, with its fluctuations, into a guaranteed entropy budget that doesn't assume yesterday's conditions will hold tomorrow. And because any seed can itself be a target, you seed from multiple weak, independent sources, small environmental feeds mixed with human keystrokes or radio hiss, and you amplify that seed through the same certified process so the final product inherits the strongest guarantee, not the weakest link. There's also a quieter battlefield. Implementations. Afterpulsing in photodetectors can mimic correlations. Power supply ripple can imprint periodicities. A field programmable chip can hide undocumented states that look random until a particular trigger reveals a deterministic backdoor. Defensive engineering treats these not as surprises but as budget items. You monitor dark counts and dead times, dither or filter clock domains, hash firmware and lock the update path, box the device against optical and RF injection, and place independent monitors that log temperatures, currents, and timing skews so that any excursion that could raise the cheater's predictive power shows up in your ledger. On top of that, you design for composability. Your random bits will feed bigger protocols, keys that guard assets, seeds that steer experiments. So the guarantee must survive being used elsewhere. Modern analyses add the uncertainties round by round with an accumulation theorem so you can stop the generator early or extend it late without breaking the security proof. And they convert the final bound into a number you can read aloud, like at least 1 million nearly uniform bits with a 1 in a billion failure chance, rather than vague comfort. Outside the lab, the same battle plays out in software. A cheater who can read or influence a general-purpose system tries to learn your seeds through logs, interrupts, or speculative execution side channels, then leans on a pseudo-random generator to expand that knowledge into your whole stream. The antidote is layered. Gather entropy in many small places that are hard to model jointly. Continuously reseed your generator, audit pool health in real time, and never conflate a fast pseudo-random stream with true unpredictability unless you can prove that the seed stayed secret. Even better, refresh that seed with certified physical bits whenever possible. Then, even if the cryptographic assumptions wobble, the fountain of entropy keeps your outputs young. There's a philosophical temptation to end the story with no method can defeat a cosmic conspiracy. But the practical lesson is sturdier. You don't need metaphysical free will to outpace a cheater. You need geometry, timing, and accounting. Geometry separates devices so local tinkering can't coordinate them. Timing ensures choices arrive too late for collusion. Accounting replaces vibes with budgets. Bits of independence in. Bits of certified unpredictability out, with every loss, drift, and bias charged to the cheater's side of the balance. The closing comfort is not romantic, but earned. A randomness oracle is not a mythic fountain, but a machine whose honesty you can audit by pitting it against games no classical schema can win well enough. A clever cheater is not a ghost, but a set of capabilities you can model and blunt. Build your system so that the only way to fake your score is to break the speed of light or to have scripted the universe eons ago, and then compress what you harvest until even a nearly omniscient adversary can do no better than guess. When the dust settles, what remains on your ledger is not just a stream of unruly bits, but a stream of promises, stated in plain numbers, backed by experiments that could fail but didn't, and strong enough to seed whatever careful future you want to secure. Schrödinger's kittens in the lab. If you want to meet the fabled paradox without myth, walk into a modern lab and ask to see the kittens, small, engineered superpositions that you can prepare, steer, and read without invoking mystery or cruelty. Because these Schrödinger's kittens are not animals, but carefully crafted field states and collective motions whose two incompatible stories are held together long enough to do work. Begin with a single electromagnetic mode, a quiet box that can ring like a wine glass, and drive it so that the resonator simultaneously holds two distinct, classical-looking vibrations pointing in opposite directions in phase space. Two bright, well-separated notes that, instead of replacing one another, add up into a single quantum state with an interference pattern hiding between them. That is a kitten. You know it's real, not because someone swears it is, but because you can probe the field gently and reconstruct a map of its statistics that shows ripples where no classical mixture would have them, the telltale fringes of both stories at once. Making and keeping such a state is a craft in itself. In superconducting circuits, you cool a chip until metal becomes nearly perfect. Carve out a high-Q cavity that traps microwave light for milliseconds, and couple it to a controllable nonlinearity that lets two photons at a time be created or destroyed. With that 2x2 handle, you can nudge the field into two mirror positions, and with feedback or engineered loss that favors pairs, keep it there against the randomizing push of the environment. In optics, you pass a faint beam through a nonlinear crystal to carve a tiny kitten from near vacuum. Then use interference with a reference beam and exquisitely efficient detectors to confirm you caught the right superposition. In trapped ions, you shake the shared motion of a small ion crystal so the whole lattice simultaneously oscillates left and right, while an internal spin ties the two motions into a single state. In mechanical platforms, you embed a membrane or a drum in an optical cavity and trade lights radiation pressure for motion, sketching the first outlines of kittens in vibrating matter. None of this is a parlor trick. The states are fragile, and the signature that proves they are superpositions, not mixtures, is an interference pattern you only see if you protect coherence from the first push to the final readout. Labs do this with two broad strategies. One is prepare and pray less. Isolate the system, do everything fast and clean, then measure before noise washes the ripples away. The other, now dominant, is prepare and protect by design. Make the environment itself stabilize the two-lobed state, so the very processes that would usually destroy coherence instead herd the field back into the cat subspace. That second path, reservoir engineering, feels like Aikido. You couple your resonator to a helper that drains away any error that would push the state off the two-note track, while errors that merely flip the relative sign are made rare or at least countable. With that in place, kittens stop being weekend curios and become building blocks. One immediate use is metrology. Because the two lobes are far apart, a tiny rotation of the state translates into a large swing in interference, letting you sense weak shifts more sharply than a single classical tone would. Another is fault-tolerant computing with bosonic codes. Here you declare the two-lobed pattern to be a logical 0 and its mirror to be a logical 1. Then watch parity. Whether the photon, count is even or odd, becomes a built-in alarm bell for a common error type. Measure that bell without collapsing the two-lobe superposition, and you can correct mistakes on the fly without destroying the stored information. This is why people talk about cats and kittens with such practical affection. They tame one of the most slippery resources, coherence, by spreading it across many excitations in a way that is both macroscopic enough to be robust and structured enough to be readable. Of course, size matters, and labs are honest about it. Kitten is not slang for cute. It's an admission that you quantify size by how far apart the two stories sit, and how bright each lobe is. In optical language, the average number of quanta in the field, and by how long the interference survives under the actual loss in your hardware. Doubling the brightness doubles the fragility. Every stray loss event whispers which lobe the field came from and blurs the ripples. That is why the march from kittens to cats is a balance of ambition and humility. You increase separation to make the two stories more classical, but you also strengthen protection and readout, so the pattern doesn't dissolve before you can use it. Verification is its own art. You don't just take a picture, you reconstruct the state statistically by sampling many quadrature angles with homodyne detection, or, in microwaves, by swapping the cavity's state into a qubit that serves as a fast, high-contrast probe. The result is a landscape with two hills and a set of alternating valleys between them, and the depth of those valleys is your audit. Too shallow, and you likely stored a mixture, not a superposition. You also perform parity maps, which light up where the interference flips sign, and run cat breeding sequences. Compositions of gates that should merge two small kittens into a bigger one, checking that the rules of interference still hold at higher brightness. The road out of the cavity is equally rich. Matter wave groups send literally large molecules through gratings and watch interference survive in vacuum. While not the same as a two-lobed field state, these experiments push quantum-like and big into new territory and drive the same engineering instincts. Clean preparation, shielded flight, efficient detection, honest counting of every run. Mechanical teams chase vibrating membranes whose motion can, in principle, be split into separated stories and then recombined. A milestone that would anchor the phrase cat state in a chunk of moving matter you could almost see. Along the way, you learn what does and doesn't buy macroscopicity. More particles is not automatically more cat. You need separation in the space of records that the environment can actually learn about. That is why a million barely separated copies tell a less striking story than a modest but well-split pair of lobes that the world would quickly distinguish if you let it. You also learn to design around specific enemies, single photon loss in cavities, phase noise in control lines, calibration drift in detectors, and slow temperature variations that warp phases over minutes. Each enemy has a counter, parity-based error correction for loss, echo sequences for phase, in situ calibration, and watchdogs for drift, feedback that nudges the cat back when it wanders. The deeper, quieter reward is pedagogical. Kittens let you watch the handshake between the microscopic rule superpositions exist and the macroscopic fact records survive. In a well-stabilized cavity, you can choose to read in a way that preserves the two-lobed structure, or in a way that writes a single classical outcome to the world. The difference is not metaphysical, it's architectural. What you couple to, how strongly, and when. If you're tempted to ask whether this rescues or refutes the old cat thought experiment, the lab's answer is neither. It replaces it. Instead of debating life and death metaphors, you learn to engineer superpositions you can audit, protect, and exploit, and to translate both at once from a slogan into a control panel with knobs you can turn. And the soft closing truth, the one that makes a long night at the cryostat feel like a story with a plot, is that kittens are not trophies for having mastered weirdness. They are tools for mastering clarity. They teach you which parts of a device must be quiet, which interactions count as writing, how to make the environment a guardian instead of a vandal, and how to convert delicate coherence into useful advantage without pretending it is anything other than delicate. In that sense, bringing Schrödinger's kittens into the lab doesn't cheapen the mystery. It domesticates it, letting you hold for a time you can choose and in a shape you can design, the very thing the old parable was always about. The power and the price of keeping two incompatible stories true until you decide, with your hands on the apparatus, which one the world will remember. Macroscopicity scales. How big is weird? Ask yourself a question that sounds simple but quickly turns slippery. If quantum strangeness shows up in everything from electrons to delicate superconducting circuits, how do you actually measure how big is weird? And what would count as progress from a single atom's interference to something your everyday intuition would call macroscopic? The honest answer is that size has to be scored, not assumed, and the scoring depends on what is put into superposition, how far apart the alternative stories are, how long the coherence is kept alive, and how decisively the data squeeze out would-be classical explanations. So researchers have built Macroscopicity scales, practical yardsticks that turn soft bragging rights into numbers you can compare across wildly different platforms. One family of yardsticks asks a very operational question. Suppose the universe had a tiny extra rule that nudged large superpositions to collapse faster. How strongly does your experiment rule out such a rule? If your interference survives, with a heavy object over a big spatial separation. For a long time, your data push those classicalizing models into a tighter corner, and you earn a higher score. In this spirit, a single atom flown for seconds through an interferometer may outscore a many-electron circuit that only maintains a subtle phase for microseconds, because the atom's center of mass superposition is a record the world could very easily have learned about, yet didn't. Another yardstick looks not outward, but inward. How many microscopic constituents are genuinely pulling together to make the observable effect? And how much metrological punch does that collectivity have? Here, measures tied to the information you could extract, how sharply the state responds to a tiny push, grade experiments by their usefulness as sensors. A perfectly choreographed group of particles whose joint phase rotates n times faster than a lone particle signals a larger, effective size than a crowd that merely hums at the same pitch as one. These two perspectives, ruling out, classicalizing tweaks, and measuring collective sensitivity, catch different aspects of big, and they explain why headlines can mislead. A superconducting loop carrying counterflowing currents encloses trillions of electrons. Yet if those electrons are locked into a single collective mode, the cat is one big degree of freedom wearing a large coat, whereas a wobbly nanosphere, placed in a superposition of two well-separated positions, with its entire center of mass is, in the relevant sense, a larger animal even if it contains fewer constituents than the circuit. With that discipline in hand, you can read the landscape without mythology. Molecule interferometry has marched from buckyballs to dye-like clusters, tens of thousands of atomic mass units heavy, sending slow, floppy objects through gratings and recovering clean fringes. The center of mass is the coordinate that matters, and the score rises because the spatial split survives for long flight times in vacuum. Atomic fountains toss clouds of ultra-cold atoms along paths, separated by meters, holding coherence for times long enough to read the tug of Earth itself. Here, the large area of the interferometer and the long dwell time feed directly into the macroscopicity measure that cares about how much opportunity the environment had to learn, which path, and yet didn't. Superconducting circuits, by contrast, excel on the collectivity metric. Cat-like microwave fields in high Q cavities spread coherence across many quanta and can be read with extraordinary contrast. Their metrological and computational figures of merit, how tightly they let you estimate a phase or protect a logical bit, are large even if their rule-out collapse score is modest, because their effective mass doesn't move in space. Mechanical systems sit between worlds. Vibrating membranes and levitated beads can, in principle, place kilogram for kilogram more matter into distinct motional states than almost anything else. The challenge is cooling and isolation so that you produce a bona fide two-story superposition rather than a classical jostle with a pretty spectrum. The point of scoring is not to crown a winner, but to guide design. If your goal is to pressure test collapse ideas, you push spatial separation, mass, and time, and you quantify exactly how your fringe visibility trims the space of alternative theories. If your goal is to build sensors or fault-tolerant logical bits, you push collective sensitivity and error detectability, and you grade by how much information per unit energy and time your state can safely carry. The scales also police loose talk. More particles is not automatically more macroscopic. A million weakly correlated quanta, behaving like a thermal fog, do not earn the same credit as a smaller but crisply split center of mass state. That would, if you removed shielding, stamp witch-path fingerprints on the surrounding air in a heartbeat. Likewise, bigger device is not automatically bigger weird. Sheet metal and cryostats add mass, not macroscopicity, unless their degrees of freedom are in play. What often decides the score is the recordability of the alternatives. The more easily the outside world could have distinguished your two stories, the more impressive it is that you kept them from leaking. That is why matter wave interferometers, with their literal left versus right paths, punch above their weight, and why internal state superpositions, while essential to quantum computing and sensing, must work harder to claim macroscopicity beyond their usefulness. The scales also give you a clean way to read progress over time. A decade ago, most macroscopicity ledgers were dominated by atomic beams and superconducting qubits. Today, levitated optomechanics has cracked into the charts. Optical cat codes are holding superpositions for milliseconds with autonomous stabilization, and molecule interferometers keep finding ways to launch bigger and floppier clusters without letting the environment eavesdrop. On the horizon are space-based matter wave experiments that extend flight times from seconds to minutes, where tiny gravitational gradients and sunlight pressure become part of the engineering rather than the noise. Whether or not they discover any deviation from ordinary quantum theory, their scores will be meaningful because the scales already tell you how to convert the raw visibility into a statement about how much classicalization pressure they resisted. There is a philosophical comfort, too, in treating how big is weird as a map rather than a verdict. The map says, choose your axis. If you care about how decisively an experiment rules out spontaneous collapse stories, follow the log-like measure that credits mass, separation, and time, and subtracts every known source of loss. If you care about how many bodies are really pulling in quantum unison, follow the information theoretic yardsticks that count collective sharpness and entanglement depth. If you care about macroscopic effect, track how much a tiny perturbation moves the needle on your readout per joule of exposure. Each axis rewards different craft: ultra-high vacuum and vibration control for matter waves, cryogenic stability and engineered dissipation for cat codes, low-loss optical access and feedback for levitated systems, and each axis excludes shortcuts that only look large from the outside. And the soft closing thought, the one that steadies your intuition when quantum but big feels like a slogan, is that macroscopicity is not a medal pinned on an object. It is a budget that your apparatus must balance. You budget separation against stability, mass against isolation, time against drift, and collectivity against control, and the scales translate that budget into a number you can defend. When you hear that something is the largest quantum state, the scales let you ask, largest by which yardstick, under which assumptions, against which alternatives, and they give you a way to celebrate real advances without confusing size with spectacle. In that sense, learning how to measure how big is weird doesn't demystify quantum mechanics so much as mature it. It replaces awe with architecture, helps you decide what to build next and why, and turns a century-old riddle into a checklist you can hold in your hand as you coax fragile, beautiful superpositions toward the scales where our everyday intuitions finally have to yield. Isolated observer on a quantum island. You arrive, alone, on a quantum island with a small lab, a clean clock and just enough power to run a few experiments. And the puzzle that sneaks up on you isn't whether the universe is strange, you already know that, but how an observer cut off from the mainland should build facts that will survive reunion later. What counts as a measurement when your only witness is you? What counts as objective when redundancy is scarce? And how you should manage memory, evidence, and energy so that the story you write on the island can be merged without contradiction into the world's larger narrative once a tiny communication channel opens. Start gently with the practical problem you face on day 1. Isolation reduces the environment's gossip, so fragile superpositions can last longer than you expect. Yet the moment you record anything, on a notepad, in your brain, as a voltage on a chip, you create an internal environment that begins to stabilize one history over its rivals. The island teaches you that collapse is not a mystical event, but a bookkeeping choice with thermodynamic footprints. Bits written, heat dumped, correlations created. Because your power and memory are finite, every observation competes with the cost of storing it, and the cost of erasing yesterday's scratchwork to make room for tomorrow's. And that forces a discipline you can dodge in a big lab. Measure only what you can afford to keep, compress what you keep so it can be verified later, and design each experiment so that the record it produces will still be useful after you leave the island. This is where the idea of objectivity gets rebuilt from parts. Off-island, facts feel solid because many independent records exist. Light scattered into the room, vibrations in the table, copies in many devices. On the island, redundancy shrinks, so you must manufacture it deliberately. Duplicate critical results in physically distinct media. Paper, flash phase flips in a protected memory. Cross-check them with independent tests that would fail in different ways, and maintain a log that ties each record to the experimental context that gave it meaning. Settings, timing, calibrations, so that future readers can reconstruct not just what you saw, but how that seeing was licensed. Suddenly, context isn't philosophy. It's a checksum for truth. Timekeeping becomes your second teacher. Without a global reference, phases drift. Clocks creep. Before and after want definitions you can demonstrate, not assume. To keep coherence meaningful and data mergeable, you build a schedule of sync events. Periodic self-calibrations that stamp your records with verifiable markers. Sideband tones, calibration fringes, known thermal loads, that mainland colleagues can reproduce and compare. Think of it as shipping future you not just answers, but yardsticks. Even your choice of measurement bases becomes strategic. You optimize for complementary questions that, together, fix the shape of the state you care about while minimizing the thermodynamic cost of recording them. You avoid over-measuring, probing the same property again and again, because redundant copies in the same medium don't buy you social objectivity later, they just warm the room today. The island also exposes a softer trap, self-confirmation. Without peers, you are alarmingly good at persuading yourself, so you design blind procedures against your own biases. Pre-commit to analysis plans, shuffle run labels so you cannot steer outcomes by fatigue, include null trials that should produce nothing, and let your software flag surprises before your narrative does. You discover that skepticism scales with isolation because the fewer external witnesses you have, the more your future credibility depends on having salted your data with ways for strangers to catch you if you fooled yourself. And then there is the puzzle of the cut between you and your lab. In a crowded world, you can slide the cut around without thinking, sometimes treating detectors as part of you, sometimes as part of it. But on the island, the cut has energy costs. Moving it inward, deciding to treat more of the setup as me, increases how much of the device you must track and stabilize, while moving it outward, letting the device write a result you later read, increases how much irreversible copying you perform. You learn to place the cut where memory and thermodynamics balance. Keep raw, reversible evolutions as long as they serve the question. Commit to an irreversible record only when the value of that record exceeds the cost to create and preserve it. That trade is not abstract. It shows up as lost battery hours and full notebooks. When the storm finally clears and the radio link to the mainland crackles open, a new problem appears. Bandwidth is scarce, so you can't ship every sample. You must ship evidence. On the island, you designed your protocols with this in mind. Instead of hoarding raw traces, you stored minimal sufficient statistics and witness tests that let others recompute your claims. Violation margins with per-trial counts. Calibration curves with reference points. Cross-validated residuals that would look different if drift, bias, or context leakage had crept in. You treated your future audience as adversarial friends. People who want you to be right, but need you to survive the attempt to be wrong. That design choice saves you now. Your first kilobytes home certify not just that something happened, but that alternative stories, classical mimicry, miscalibrations, selection, were tested and lost. The island also reframes state as a personal asset with market rules. Before you transmit, your best description of the system lives inside your head and devices. After you transmit, that description will be merged with others. To make the merge clean, you prepare to translate your internal state into statements that are invariant under reasonable changes of description. Likelihoods that attach to recorded contexts rather than private mental models. Error bars that reflect finite sampling rather than wishful limits. And protocols for updating that you and others would both accept. In the quiet hours, you've practiced this. Rerunning old data through new hypotheses to ensure your bookkeeping supports reanalysis without your supervision. Even the island's loneliness teaches a physics lesson about meaning. With little environment, you can preserve delicate alternatives. But without redundant witnesses, your facts are exactly as strong as the records you keep. There is no shortcut in which the universe guarantees that your private observation is a public truth. Objectivity is engineered by replication and cross-checks, not granted by metaphysics. Yet neither is solitude sterile. It sharpens what must be recorded for later agreement, and what can remain an internal guide. And so your last week is spent doing something that will look unromantic in a textbook, but heroic to anyone who has wrestled with data. You stress your own story. You vary temperature to map drifts. You leave the system idle to verify baselines. You scramble labels. You won't unscramble until after transmission. You simulate failure modes and confirm your witnesses would have caught them. You measure across incompatible contexts in complementary blocks to ensure no hidden signaling could have linked them. And you pre-compute merge-friendly summaries so that when the first packets reach a distant server, strangers can reproduce your gates from the logs alone. When the skiff arrives at last and your island becomes a dot astern, you realize the lesson was never about being first to see a fragile fringe. It was about learning how an observation becomes a shareable asset in a world that cannot look inside your head. The calm closing thought you carry home is simple and durable. An isolated observer is not a mystical agent, but a careful accountant, the keeper of clocks, contexts, and costs, who learns to convert private encounters with a quantum system into public evidence by designing experiments that write the fewest, strongest records by paying honestly for every erased bit, by pre-building the checks that a skeptical audience will need, and by accepting that reality at human scales is the network of records we can agree upon when we finally plug back in. The last measurement, who reads the tape, start not with a cat or a paradox, but with a plain recorder rolling beside a quiet apparatus. A probe nudges a system, a detector flips, an amplifier shouts a little, an analog trace steps into digits, and the digits flow onto a storage tape. So the sober question isn't what collapses the wave, but when does this string of operations become a fact anyone can stand on? And, underneath that, who has to read the tape for the fact to count? The calm, unglamorous answer is that what we call the last measurement is not a mystical moment owned by a special observer. It's the point in the chain where a physical record becomes stable, redundant, and legible enough that independent readers, human or machine, could, in principle, recover it and agree about what action it licenses next. Begin with the mechanics before the metaphors. A measurement is a controlled coupling that correlates a microscopic variable with a macroscopic pointer, and then with many pointers, voltages in a preamp, bits in a buffer, entries in a file, photons scattered into the room, so that the alternatives that once could interfere now feed into disjoint macroscopic states that almost never rejoin. The tape stands for that growing web of records. The first flips are reversible in principle, but as amplification and copying proceed, the record spreads into so many degrees of freedom that reversing would require an astronomically specific undoing. In practice, irreversibility is the moment you permit uncontrolled redundancy. That is why no single person's look is required, and why a robot can close the loop. What matters is not consciousness but architecture. How the device fans a microscopic difference into a persistent, checkable pattern, yet persistent and checkable, has content. If the tape is a single fragile file on a drive with no metadata, no synchronization, and no checksum, you have not reached a last measurement in the operational sense. You have a volatile note that could be rewritten by drift or error. To push a result across the line into a scientific fact, you deliberately add scaffolding, timestamps tied to a traceable clock, calibration blocks interleaved with data blocks, parity or hash codes to detect corruption, and cross-recording on independent media, so a single failure mode does not silently rewrite history. You also store the context that makes the number meaningful: settings, delays, detector thresholds, environmental monitors, because without the recipe, the number is not a fact about the system, it's an orphan. At this point, the tape could be read by you tomorrow, or by a stranger next year, and, given the metadata, both would reconstruct the same claim. Notice how "who reads" has become "who could read," which is exactly the shift from private seeing to public evidence. Now for the uncomfortable edge cases that make this more than bookkeeping. Suppose the apparatus runs overnight, writes a beautiful record, and burns before anyone opens the file. Did the measurement happen? As physics, yes. A macroscopic record existed and influenced other variables while it did. As science, no. A fact that cannot be recovered or audited, cannot guide future action. And in our practice, fact is tied to reproducible access, not metaphysical existence. Suppose the tape is read by an algorithm that flags outliers and triggers feedback pulses that steer the next round, while no human watches until the end. Is the algorithm the last measurer? Not in the sense of a special status. It is one more reader in the redundancy network, and what matters is that its decisions are logged with enough detail that you can later audit, whether the feedback biased the statistics, whether the thresholds drifted, whether the algorithm silently learned features you did not intend. This is why mature experiments treat readout as a protocol, not a peak. You pre-commit to when a run ends, which branches will be copied and how, which summaries will be kept, and which raw slices are archived for independent checks. You build tape readers into the design, checksums, control channels, calibration shots that will catch you if your own eagerness leads you to overinterpret. The deeper tension hides in a deceptively simple question. Can you ever identify a unique last measurement, a final place where you must draw the line? In principle, you can slide the line, include the oscilloscope as part of the system, and treat your eyes as the reader. Include your brain and treat the written log as the reader. Include the repository and treat the journal referee as the reader. Each move adds more of the downstream world to the apparatus. And the physics doesn't blink because nothing privileged happens at any one cut. In practice, though, you do choose a stopping rule, and it is always operational. Stop when the record is sufficiently redundant, when further copying only adds cost and risk, when the marginal benefit to future agreement is below the marginal thermodynamic and logistical expense. That rule has teeth. Copying consumes energy and opens attack surfaces. Cosmic rays in memory, bit flips on disks, calibration drift while you're still writing. So, last measurement is also a resource allocation problem. You invest until the chance of later disagreement is below a bound you can live with. Then you seal the run. The tape metaphor helps discipline your language about collapse too. The microscopic theory predicts reversible evolution for system plus apparatus plus environment. The irreversible look of outcomes is tied to record proliferation and to your refusal, sensible, necessary, to attempt a colossal rephasing of the scattered copies. Reading the tape is just the act of making one more copy, but the important copies are those that change behavior, trigger a gate, update a model, publish a result. That is why the last measurement is inseparable from decision. A number that no one uses is a curiosity. A number that routes the next pulse, trips a safety interlock, or becomes a line in the ledger is a fact. With that in mind, a clean design for the end of an experiment features 3 pieces. A sign-off test that shows the record is internally consistent and externally cross-checked. A compact summary that a skeptical outsider could recompute from the stored context. And an audit trail that makes tampering or self-deception unlikely to pass unnoticed. None of these pieces requires a specific who, Only a set of readers, present or future, who share the rules. The last measurement question then softens into a design principle for any laboratory or sensor network. Build your apparatus so that a microscopic difference becomes a robust, low-ambiguity record. Tie that record to clocks and controls that others can verify. Decide in advance when redundancy exceeds risk. And treat every read not as an act that metaphysically creates a fact, but as one more link in a chain, whose strength lies in the possibility of many readers agreeing after the fact. The gentle closing thought is that this principle scales beyond physics. In a world soaked with data, the meaningful events are the ones that survive being read by strangers across time. The rest are sparks that never catch. Who reads the tape? Anyone you equip to do so. When does the reading end? When additional eyes add confidence more slowly than they add noise. And what makes the tape worth reading at all? That it was written with enough honesty and context that your future self, or someone who doubts you, can press play and hear the same quiet answer the device whispered the first time. Branch counting versus born rule. Open with a bait that sounds fair but hides a trap. If the universe really branches when measurements happen, shouldn't you just count the branches and call each one equally likely? After all, more branches means more ways the future can go. Yet the moment you try to live by that rule, the floor drops away. Because how many branches is not a physical invariant while the born rule's weighting is. And the difference between head count and measure is the difference between a story you can redraw by fiddling the scenery and a law that survives every honest redescription of the experiment. Start from the plumbing, not the poetry. A lab measurement doesn't produce a few tidy worlds. It couples a simple system to an amplifier and then to an enormous environment. Air, photons, vibrations, memory, and decoherence scatters microscopic distinctions into a billion microscopic records in fractions of a blink. What you might call one outcome is actually a fuzzy bush of microhistories whose twigs differ in details you neither control nor care about. The exact time a thermal photon bounced, the precise phase drift of a cable, the order in which molecules hit a mirror. If you try to count branches, you must first decide which microhistories are the same branch. But there is no unique way to do that. Change the coarseness of your description or the basis you use to define sameness, and the tally swings wildly. Worse, you can manipulate the count without touching what anyone observes. Add a harmless gadget that jiggles the environment differently in one outcome than another, and the number of branches changes even though every detector you deem relevant reports the same frequencies. A probability rule that flips when you add a decorative fan to the wall is not a rule you can defend. The Born rule, by contrast, attaches to the amplitude weights that quantum dynamics preserves no matter how you slice the environment. Unitary evolution shuffles these weights without creating or destroying their total, and decoherence pushes them into almost disjoint packets that travel forward like independent histories. That is why weight behaves like a conserved budget, while branch count behaves like the number of leaves you decide to notice. To see the practical stakes, imagine two outcomes with weights in a 2-to-1 ratio. In a typical amplifier, the heavier outcome quickly sprouts an astronomically larger bush of microbranches than the lighter one, because more microscopic stories are compatible with its macroscopic record, but nothing forces the ratio of bush sizes to match the squared amplitudes. Small engineering choices can sway the counts. If you insist on head count, a bookie can make you prefer bets that depend on irrelevant micro-jitters, how many dust specks scattered which way, over bets that track the robust record your instruments actually store. In contrast, a rule that follows the conserved weights remains stable when you refine or coarsen your description, whether you group twigs into boughs or split boughs into twigs. The total weight assigned to "this dial reads high" stays the same, and the empirical content of quantum theory, what frequencies you and your colleagues collectively see, lines up with that weight across every experiment we know how to do. This stability under regrouping is not a philosophical taste, it's a test. A sensible probability assignment should respect three requirements that branch counting flunks. First, invariance under harmless refinements. If you take a single outcome and split it into many micro-variations that your readout cannot distinguish, the assigned probability should not change. Branch counts explode. Weights don't. Second, additivity under coarse graining. If two exclusive outcomes are lumped into either, the probability of either should be the sum of their probabilities. Weights add cleanly. Counts can be double counted or shaved, depending on which microhistories you decide are really the same. Third, symmetry under relabeling. If two outcomes are physically interchangeable apart from a unitary shuffle of degrees of freedom, your assignments should be the same. Amplitude weights are blind to the labels, while counts can be driven by bookkeeping choices that live only in your notebook. You can dress these requirements as geometry rather than rules. The Hilbert space that carries the dynamics comes with a natural notion of volume, the squared length of the state's components, and that volume is what unitary evolution preserves. If you think of picking an outcome as sampling a point from the set of observer records consistent with the state, the only sampling method that is independent of how you carve the set into bins is the one that uses this preserved volume. Any other sampling depends on arbitrary bin edges. This geometric view is a different door into the same room as other arguments. Frequency typicality across many runs, symmetry-based derivations, and decision-theoretic coherence, but it stays clear of preferences or gambling talk and simply asks for a rule that does not wobble when you change the magnification on the microscope. There is also a clean operational audit you can run in your head. Imagine building a branch counter that tries to tally distinct histories by looking for tiny environmental differences. Move the threshold a little. Call two twigs different only if some minute field crosses a slightly higher level, and the count swings. Worse, the counter becomes part of the apparatus, so the act of counting back reacts on which tiny differences exist at all. Now build a weight meter. Let the system evolve and read the relative frequencies of outcomes in large ensembles where decoherence has already quarantined alternatives. Those frequencies agree to the accuracy of your statistics, regardless of whether you micromanage the environment. The first gadget is a Rorschach test for your modeling choices. The second is what every laboratory already does when it reports a branching ratio. There is a human temptation here worth resisting. Headcount feels democratic because it declares every future you equal, while the Born rule feels elitist because it makes some futures thicker than others. But physics is not voting, it is prediction. When you plan experiments, you implicitly trust the weighting that makes retrodictions and forecasts come out right. Detector logs over countless trials march toward the squared amplitude ratios, and agents who place their expectations elsewhere will read their own notebooks as records of systematic disappointment. If you want a more visceral analogy, trade worlds for sentences. A theory's predictions are not the number of sentences you can write about an outcome. They are the clarity of the signal in the data stream that outcome would produce. You can always write more sentences, but you cannot increase the weight of evidence they summarize. In the same way, you can always carve more branches out of the air by changing your definitions, but you cannot change the amplitude weight that flows into records the environment will stubbornly keep. Perhaps the deepest reason branch counting fails is that branching is a story we tell about decohered structure at a particular level of description, not a fundamental operation that nature performs with integer steps. What is fundamental is the linear, norm-preserving flow of the state and the emergence of robust records that refuse to interfere. Where those records form, you may speak of worlds. Where they do not, counting worlds is like counting clouds. The Born rule latches onto the part that doesn't evaporate when you change the weather. So the calm closing counsel is this. When you stand at a quantum fork, do not ask how many trails, but how wide is each trail in the geometry the dynamics preserves, because width, not the number of times you decide to trace. The path with a pencil is what controls which futures are typical in your data, which expectations stay calibrated, and which stories survive being told by many independent witnesses. If you keep that compass, branching becomes an honest bookkeeping device, not a lottery. And the Born rule stops being an edict from nowhere and becomes what it has quietly been all along. The unique way to keep probability tied to structure when the universe insists on offering more than one way things can go. Collapse timing. When did it happen? Ask the question as if you were marking a logbook after the fact. When did the collapse happen exactly? And you'll feel the floor tilt because the sense that there must be a single, sharp moment gives way to 3 different clocks that rarely tick in unison. The clock of your instrument, when a threshold crosses and you stamp a time. The clock of inference, when the total evidence justifies treating alternatives as settled. And the clock of dynamics, how the system, apparatus, and environment actually braid together during the measurement chain. Start with the instrument's clock because it's the one people reach for first. In a photodetector, for example, a single carrier can trigger an avalanche that rises for a few billionths of a second before your electronics call it a click. That timestamp is precise enough for lab work, but it's not the moment a tidy microscopic change turned into a macroscopic fact. It's the moment your amplifier promised, you can now act on this. In a cloud chamber, a track forms across many collisions. Which droplet counts as the instant of collapse? Your file will show a first frame, but that frame is an arbitrary cross-section of a process that gained redundancy gradually. Now move to the clock of inference, which is where the everyday meaning of happened lives. In weak, continuous monitoring, each sliver of data, each tiny deflection of a probe, barely shifts your belief. Only after enough slivers accumulate does your posterior confidence surge past the gut-level threshold where you say, okay, the state has jumped. That surge can precede the hardware threshold if you combine many noisy hints. Even no click yet is a hint. Or it can lag if you demand conservatism. The point is that collapse, understood as the moment you start behaving as if one alternative is true and the others are irrelevant, is a decision rule tied to evidence, not a microsecond engraved in nature. Finally, consider the clock of dynamics, where you follow the system's coupling to the apparatus and then to the environment. Decoherence, the leakage of which record information into uncontrolled degrees of freedom, doesn't arrive like a hammer. It swells, often ultra-fast, as scattered photons, phonons, and charges spread the correlation. Within a time window set by that swell, the alternatives that could have interfered in principle become practically unrecoverable. If you insist on a single answer, the honest one is a band, long enough for redundancy to bloom, short enough that reversing it would require cosmic choreography. Now layer relativity on top and the urge for a unique timestamp evaporates completely. When 2 labs separated in space record entangled outcomes, space-time allows frames in which A's record is earlier and frames in which B's is earlier. No experiment ever reveals a contradiction, because the joint statistics respect light cone causality. Ask which collapse came first, and you are really asking for a preferred foliation the physics does not provide. Ask when did each lab gain enough local evidence to treat its outcome as settled, and you get frame-consistent answers tied to local clocks and signals. This is why delayed choice experiments are not time machines. Deciding late which question to ask does not rewrite earlier records. It decides which kind of record will ever exist, and so it determines which alternatives decoherence will suppress. The past you care about becomes definite only to the extent you built a context that writes it. There is a deeper subtlety that modern experiments lay bare. With continuous monitoring, you can watch quantum trajectories, those jittery paths by which a state meanders and occasionally jumps. Sometimes you see a jump announce itself not by a sudden click, but by the absence of expected clicks, as when a fluorescing atom goes dark. The missing photons are information, and your state estimate slides accordingly before any threshold fires. Sometimes you smooth by using data from a short time after an event to sharpen your estimate of when the change most likely occurred. The refined estimate moves earlier, but you have not sent a message to the past. You have simply folded more evidence into a timeline that was always fuzzy. In each case, the collapse time you report is an inference tied to a model of how signals arise. Change the model, include slower filters, add latency, tighten or relax your priors, and the assigned time shifts while the underlying causal story remains the same. If your taste runs to objective collapse proposals, those that posit an extra law that forces macroscopic superpositions to localize with a definite rate, then the question, when did it happen, acquires a different flavor. The answer is stochastically, with a rate set by mass, separation, or other parameters. Crucially, that answer is testable. Interference of large molecules, levitated beads, and long-arm atom interferometers carve out regions of parameter space where such extra collapses would have smeared the fringe but didn't. In that framework, when is a draw from a physical hazard function. In standard quantum theory with decoherence by contrast, when is a matter of how fast records proliferate and how you, as a user of the record, choose to treat near certainty as certainty. These perspectives are not enemies, they are lenses. The practical art is to keep them straight. When you publish a timestamp, make clear it's an instrument time with jitter and latency. When you say an event occurred at TT, mean that your pre-declared analysis would have made the same call for any reader holding your data at that TT, not that the universe flipped a metaphysical switch there. When you design an apparatus, decide how quickly you need alternatives to become inert for the task at hand. Fast for real-time feedback, slow if you want to watch a trajectory, and engineer the coupling and the environment accordingly. And when conversations drift toward philosophy, steer them back to operational statements that experiments can arbitrate. How early can we assign a reliable label? How does that depend on probe strength, loss, and model? And how do independent readers, with access to the same logs, agree on a timeline within quoted error bars? The gentle closing thought is that collapse timing is not a singular secret hidden in the data. It is a contract between dynamics, evidence, and use. Nature supplies decoherence rates and causal structure. Your apparatus supplies thresholds and latency. Your analysis supplies the rule that turns a probability curve into a verdict. Ask when with that contract in mind, and you get answers that travel well across labs and frames. Ask when, as if there had to be a single, sacred tick, and you will keep chasing your own timestamp through the very chain of amplifiers and copies that gave you the power to ask in the first place. What a world means carefully. Say world too quickly, and you smuggle a picture into the room, a crisp, countable set of parallel universes marching like pages in a flipbook. So slow the word down until it earns its keep. A world, carefully, is not an ethereal duplicate that pops into existence with a drum roll, but a dynamically autonomous pattern of records that has become so redundant and so hard to unmake that it behaves, for all practical and communicable purposes, like a classical history with its own stable furniture. And the craft is learning to point to those patterns without pretending they are carved into nature with a cosmic chisel. Start with the humdrum ingredients that actually give you a world, systems that interact, devices that amplify, environments that gossip by scattering light and jostling air, and observers, human or robotic, that write and rewrite summaries. As interactions spread, some properties imprint themselves over and over in many places. The angle of a pointer etched into camera pixels, tiny phase kicks in surrounding photons, heat deposited in a coil, so that any one imprint can fail and the others still proclaim the same story. And it is this redundancy that turns a delicate micro-event into robust public fact. A world is the network woven by those mutually reinforcing records. Not a single perfect photograph, but an album of overlapping snapshots taken from different angles that agree on what happened well enough that future predictions can be made and checked without having to track every microscopic vibration. That independence from micro-portraits is crucial, because the fine details keep evolving reversibly underneath. What matters for worldhood is that the coarse summaries, pointer left or right, dot here or there, have become dynamically decoupled, so you could try for 1,000 lifetimes to coax their alternatives back into interference, and you'd fail for practical reasons that matter. Not because of a veto from the heavens, but because you would need to collect and reverse every scattered whisper in the room, every glow in the walls, every neuron that twitched when a lab tech glanced at the screen. The same caution reshapes what counts as a boundary. In cartoons, worlds split with a click, but in honest setups, branching is a spread, a bloom of near-disjoint stories that separate as records proliferate. Before the bloom, alternatives still crosstalk in principle. After the bloom, they are like boats that have drifted so far apart on choppy water that no captain can steer them back together. Where you draw the line between still one and now two depends on your coarse graining, how much variation you treat as the same story, how much noise you tolerate before a record counts as changed, how you define the same apparatus over time. That dependence is not a weakness, it is the content of the claim. A world is a pattern at the level where agency and prediction live. And like the concept a storm or a traffic jam, it has fuzzy edges that do not stop it from being real. Ask a different question, say one that cares about a molecule's phase rather than a dial reading, and you activate a different partition, one in which the worlds track other summaries, switch instruments, and the boundaries move. This is why responsible talk avoids counting worlds as if they were beads. The very act of defining what counts as a distinct world requires you to declare which records and which tolerances matter, and you can always subdivide or merge stories by changing that declaration. What doesn't change is the weight carried by those stories in the underlying dynamics and the degree to which they are shielded from mutual interference once the environment has echoed them. And because a world is an autonomous pattern, not a metaphysical substance, it inherits all the mundane duties of autonomy. It must carry its own memory forward. It must support agents who act on the records it contains. And it must be able to ignore tiny perturbations that don't rewrite those records. This gives you a checklist that is more than philosophy. First, redundancy. Are many independent fragments of the environment readable in ways that agree on the same macroscopic facts? Second, stability. Do those facts survive being copied, compressed, and used as inputs to future control without unraveling? Third, locality of influence. Does predicting tomorrow's coarse features require only today's coarse features plus short-range information, or must you model unreachable micro-correlations? Fourth, auditability. Could distant observers, who later collect your logs, reconstruct the same narrative to within the declared tolerances? When the answer to these questions is yes, you have something that earns the everyday name world. And when the answer is no, you have an unstable prelude, a context-dependent limbo that has not yet cashed out into public fact. Notice how this reframing tames familiar anxieties. You need not decide whether worlds are created when people look. The redundancy that matters is written largely in the environment long before any human reads it. Sunlight bouncing off a leaf, phonons racing through a table, electrons locking a sensor bit. You need not hunt for a single metaphysical instant of fission. The growth of autonomy is continuous, and your timestamps reflect thresholds you chose in your analysis, not a cosmic bell. You need not fear that shifting your description erases reality. It only changes which patterns are salient, like viewing the same coastline on different maps. And you need not be seduced by the drama of infinite multiplicity. Talk of countless worlds is just a shorthand for the fact that the environment can and does support countless distinct, mutually stable patterns of records when devices and contexts demand them. This sober view also clarifies responsibility, because a world is a record pattern, not a prize for a particular favorite story. Your modeling obligations are operational. Specify which summaries you treat as factual. Specify how they are extracted from raw signals. Specify the tolerances for agreement, and specify how conflicting records will be adjudicated. In computing and metrology, that looks like building sensors and error-correcting codes that keep macroscopic summaries intact while allowing microscopic mistakes to be detected and repaired. In foundations, it looks like preferring statements that survive under different coarse grainings to ones that depend on a special vantage. Even ethics gets a foothold. If worlds are record patterns, then planning under uncertainty is about shaping those patterns across time, choosing experiments, protocols, and safeguards that maximize the number of robust futures in which projects complete and obligations are honored, rather than fantasizing about hopping between finished biographies. Finally, beware of two easy misreads. One says that if world boundaries are fuzzy, worlds aren't real. By that standard, clouds and economies are unreal too, yet they carry weight because their patterns control action. The other says that because you can define many partitions, any story goes. But partitions are not free-form poetry. They are constrained by what the environment actually records, and by which summaries remain predictive. The reason you and I agree on the broad outline of yesterday is not that we love the same metaphors. It is that thousands of independent traces, photos, receipts, memories, wear marks, mutually reinforce a narrow family of narratives. Call that family a world if you like, and be clear that the word names a successful compression, a stable scaffold for agency, a platform on which curiosity can push forward without constantly consulting the microscopic oracle. The soft closing thought is therefore less cosmic than practical. Treat world as a promise your descriptions make to your future self and to others. That the records you elevate will remain legible, that their boundaries won't jump under small perturbations, and that the predictions you anchor on them will survive a second reading by different minds and different tools. Keep that promise, and you can talk about worlds without mythology. Break it, and the word becomes a costume that slips the moment the lights come up.